Somewhere in the depths of space, a black hole may be doing the unthinkable, not just consuming everything in its path, but unleashing a laser-like beam of pure energy. Not crafted by technology, but formed by the raw, chaotic forces of space-time and quantum mechanics. A phenomenon so strange, so theoretical, it blurs the line between science and the unimaginable. No signals. No warnings. Just a silent force waiting in the cosmic dark. This is the mystery of black hole lasers, a concept so powerful, it could redefine our understanding of the universe itself. But before we continue, subscribe to the channel so you don't miss out any of these videos. It sounds like something from the fringes of sci-fi. A laser powered by a black hole? One that doesn't just shine, but potentially amplifies quantum fluctuations into roaring beams of radiation, piercing the darkness of space with a whisper from the fabric of reality itself? This isn't fantasy. It's a real, theoretical concept, one that emerges from the deeply tangled world of quantum mechanics, general relativity, and the physics of extreme environments. This is the story of black hole lasers, a theoretical prediction that bends the rules of what we think is possible. If true, it would redefine our understanding of both black holes and the quantum vacuum that surrounds them. But to understand this, we need to go far, far beyond what we know about lasers. Far beyond what we think we know about black holes. And far into the weirdest intersections of physics. So buckle in, because we're about to embark on a journey that fuses the most powerful forces in the universe with one of the most revolutionary ideas in modern physics. Let's start with a basic but essential paradox that continues to plague our understanding of reality. The paradox that begins at the event horizon of a black hole. You've probably heard of Hawking radiation, that black holes aren't entirely black. They slowly leak radiation due to quantum fluctuations near the event horizon. But Hawking's idea led to something even stranger. If a black hole can emit radiation due to quantum effects, could that process be controlled, enhanced, or, dare we say, engineered by nature into something resembling a laser? Enter the wild idea proposed by physicists like Stefano Liberati and Ulf Leonhardt. They described what is now called a black hole laser. And to grasp how truly strange this idea is, we have to break apart our intuition. Because the deeper you go, the less familiar everything becomes. In traditional lasers, light is amplified in a cavity, a space where photons bounce between mirrors, being stimulated until they emerge as a coherent beam. Now imagine a similar cavity not made by glass and metal, but by the warping of space-time itself. Imagine a region around the black hole, or even inside a rotating one, where the properties of space-time act like reflective boundaries for quantum waves. Instead of bouncing photons, we're talking about quantum excitations trapped between two horizons. Yes, two horizons. Because here's the wild part, in certain exotic configurations, especially in analog black holes or rotating astrophysical black holes, you can have more than one horizon. There can be an inner horizon and an outer horizon. And under just the right conditions, those two can form a cavity. A quantum trap. A natural amplifier. In this bizarre space-time cavity, quantum fluctuations don't just flicker and vanish, they echo. They reflect. They grow. With each bounce, they're amplified, just like light in a traditional laser cavity. This feedback loop can, in theory, lead to an exponential buildup of radiation, like a screaming whisper from the vacuum itself. This is the essence of the black hole laser. But to really appreciate how profound this is, we need to look at how this idea emerged, not just from black holes themselves, but from an entirely unexpected field, fluid dynamics. In the early 2000s, physicists realized they could simulate the behavior of black holes in the lab using moving fluids. That's right, water and sound. In what are called analog gravity systems, researchers created flow patterns in fluids that mimic the event horizon of a black hole, not for light, but for sound waves. Imagine a river flowing faster than the speed of sound. At a certain point, sound can no longer travel upstream, just like light can't escape a black hole. That point is a sonic event horizon. And this is where the theory of black hole lasers found new life. In these analog systems, scientists discovered that if you have a region where the flow slows down again, a sort of anti-horizon, you get two sonic horizons. And in between them, sound waves can get trapped and amplified. These were the first laboratory glimpses of the black hole laser effect, not in the sky, but in tanks of flowing fluid. This gave physicists a playground to test theories about radiation from black holes in a totally new way. The results were surprising. In these lab-made sonic black holes, researchers observed the emission of correlated phonons, sound wave particles, that mimic the expected behavior of Hawking radiation. And more importantly, under the right conditions, these phonons grew in amplitude, forming a pattern astonishingly similar to laser emission. Now, here's where things get truly eerie. If such a mechanism exists in analog gravity, why wouldn't the same mechanism operate in real gravitational systems? The concept of a black hole laser quickly expanded beyond just fluids. It became a serious idea in quantum field theory and curved spacetime, a field that attempts to understand how quantum physics works in strong gravitational backgrounds. Researchers explored rotating black holes, known as curved black holes, and discovered they could also form similar cavities under certain energy and angular momentum conditions. In some configurations, these cavities could trap scalar fields, quantum fields with no spin, and allow them to reflect between horizons, building up like pressure in a cosmic kettle. This process could, in principle, result in emissions that resemble a laser beam, not coherent visible light, but powerful, focused beams of quantum radiation. Some theorists even suggested that this mechanism could explain certain mysterious emissions observed in the universe, bursts of energy that don't easily fit known astrophysical processes. Now pause and consider this. If black holes can act like lasers, what does that mean for the role of information, entropy, and the laws of thermodynamics in extreme gravity? What does that mean for our models of the universe's birth and death? Because here's the kicker, black hole lasers aren't just theoretical curiosities. They touch every major question in fundamental physics. From the nature of spacetime to the behavior of information. From the arrow of time to the boundary between classical and quantum realms. And it all begins with that simplest of questions, what happens to light, and to the vacuum, when gravity takes the stage? To understand the idea of a black hole laser, we need to start by thinking about two of the most powerful and paradoxical forces in physics, gravity and quantum mechanics. Black holes represent the ultimate triumph of gravity. They are regions of space where gravity is so intense that nothing, not even light, can escape. They form when massive stars collapse under their own weight, compressing all their matter into an incredibly small region known as a singularity. Around this singularity is the event horizon, the point of no return. Once something crosses it, it's gone, absorbed forever into the dark heart of the black hole. But here's where the story gets strange. While classical physics paints black holes as inescapable prisons, quantum mechanics sees something very different. In the 1970s, Stephen Hawking shocked the scientific world by proposing that black holes aren't entirely black. Instead, due to quantum fluctuations near the event horizon, they can emit radiation, now called Hawking radiation. This phenomenon arises from the creation of virtual particle pairs at the edge of the black hole. One particle falls in, the other escapes, making it seem like the black hole is evaporating over time. This concept is critical because it reveals that black holes are not eternal. Over immense periods of time, they could slowly lose mass and eventually vanish. But it also raises profound questions. If black holes can emit radiation, can that emission be manipulated or amplified? Can the quantum vacuum around a black hole be engineered, at least theoretically, to behave like the medium inside a laser? That's where the idea of black hole lasers comes in. In traditional lasers, light is amplified through a process called stimulated emission. You start with atoms in an excited state, meaning they have more energy than usual. When a photon of the right energy comes along, it can cause those atoms to release their extra energy in the form of identical photons. These photons are coherent, they have the same frequency, direction, and phase. Mirrors at either end of the laser bounce the photons back and forth, stimulating more emissions, until a powerful, focused beam of light bursts out. Now imagine a black hole acting like one of those mirrors, not a literal mirror, but a boundary where quantum effects are so intense that they reflect and amplify waves in a very specific way. Instead of photons bouncing between two glass surfaces, you have quantum field fluctuations bouncing between two gravitational boundaries. One of those boundaries is the event horizon of a black hole. The other is something even stranger, a white hole. White holes are the hypothetical opposites of black holes. Where a black hole allows nothing to escape, a white hole allows nothing to enter. It's as if time runs backward. Matter and energy erupt from it, but can never go back in. So far, no white holes have been observed in the universe, but the equations of general relativity allow for their existence. And that's important, because in the theoretical framework of a black hole laser, you need both. Here's the setup. Imagine a region of space where a black hole and a white hole are connected. This forms a kind of gravitational trap, a pocket of curved space where light or other quantum fluctuations can bounce back and forth. As these fluctuations reflect off the horizons, they can gain energy, just like photons in a traditional laser gain energy as they bounce between mirrors. And if the conditions are just right, those fluctuations can amplify into something intense, a beam of radiation, squeezed out from the quantum vacuum itself, radiating away from this exotic gravitational cavity. That's the black hole laser. This scenario isn't just some wild guess. It has mathematical support. In the late 1990s and early 2000s, physicists like William Unruh explored these ideas using something called analog gravity. Instead of looking at actual black holes, which are almost impossible to experiment with directly, they built laboratory systems that mimic black hole conditions. One famous example uses flowing fluids or Bose-Einstein condensates, materials cooled to near absolute zero that behave according to quantum principles. When the flow of the fluid changes rapidly, like water speeding up past a point in a pipe, you can simulate an event horizon. And in these setups, under the right conditions, researchers have observed something resembling Hawking radiation. More interestingly, they've observed amplification effects that closely mirror what a black hole laser would theoretically produce. These analog experiments suggest that the concept isn't just math, it has roots in physical systems. That opens up staggering possibilities. Could black hole lasers actually exist in nature? Could they form in certain exotic cosmic environments where space-time is curved just right? Could they be responsible for some of the unexplained high-energy phenomena we see in the universe, like gamma-ray bursts or fast radio bursts? These are open questions, but the black hole laser idea offers a tantalizing potential explanation. What's truly astonishing about this concept is how it unites so many different aspects of physics. You have general relativity describing the curved spacetime around black and white holes. You have quantum field theory describing how particles behave in that spacetime. You have thermodynamics through Hawking radiation. And you have optical physics through the laser analogy. It's like every corner of physics is whispering a piece of the puzzle. As we continue exploring this topic, we'll go even deeper into the mechanics of how these theoretical lasers could work, how they relate to superradiance, what the experimental analogs look like, and what all this means for our understanding of the cosmos. We'll explore the origins of the black hole laser theory, the people behind it, the math that powers it, the controversies surrounding it, and the enormous implications it holds, not just for physics, but for the very nature of reality. In traditional lasers, light amplification is achieved by stimulating photons to bounce back and forth between mirrors inside a cavity filled with a gain medium, typically a gas, crystal, or semiconductor. The process depends on a principle called stimulated emission, where an incoming photon causes an excited atom to drop to a lower energy state and emit a second photon that is coherent with the first. These photons then bounce between the mirrors, growing stronger until they form a concentrated beam of light. Now, imagine that principle applied not in a lab, but in the warped spacetime near a black hole. Instead of mirrors, the structure involves gravitational boundaries. Instead of atoms and photons, the system amplifies quantum fields. And instead of being confined to a tiny box, the laser cavity stretches across cosmic distances, defined by event horizons and other exotic surfaces like the inner horizon of a rotating black hole. The first theoretical model of a black hole laser was proposed in the early 2000s by physicists, including Stefano Corley and Ted Jacobson. They were inspired by a curious analogy between the behavior of light and optical fibers and sound in moving fluids, both of which can be used to simulate the behavior of particles in curved spacetime. Their idea was this: under the right conditions, a black hole could form a natural cavity, trapping certain types of waves in a region bounded by two horizons. These waves, most often modeled as sound-like excitations in theoretical analogs, could bounce back and forth and be amplified in much the same way light is amplified in a traditional laser. This amplification would be fueled by a process similar to Hawking radiation, where vacuum fluctuations give rise to real particles. But instead of simply escaping into space, these fluctuations would be reflected and contained between two boundaries. In the rotating case, this can happen between the inner and outer horizons of a curved black hole. The inner horizon, where strange phenomena like negative energy states can exist, acts as a reflective surface. Waves trapped between this inner horizon and the outer one can undergo repeated amplification. Each time the wave reflects off one horizon, it gains energy from the black hole's rotation or gravitational potential. This is akin to superradiance, a known effect where waves scattered by a rotating black hole come out with more energy than they went in. If these waves are reflected multiple times, like photons bouncing between mirrors, they can grow exponentially, leading to a cascade of amplified radiation, a black hole laser. This process is purely theoretical at the moment. It hasn't been observed in nature or in astrophysical data. But the mathematics that underpins it is tantalizing. It emerges from general relativity combined with quantum field theory in curved spacetime, a notoriously difficult domain that's filled with paradoxes, such as the information loss problem and the firewall paradox. The fact that such a system might produce coherent radiation suggests that black holes, far from being silent absorbers of matter, might host complex internal dynamics that we've only just begun to glimpse. What makes black hole lasers even more fascinating is that similar principles can be tested right here on Earth, not with real black holes, but with analog systems. In the lab, scientists have built sonic black holes using Bose-Einstein condensates, which are ultra-cold states of matter where particles behave like a single quantum entity. In these condensates, it's possible to create regions where sound cannot escape, mimicking an event horizon. By carefully controlling the flow and density of the condensate, researchers have built laboratory analogs that reflect the basic physics of black holes. And in these systems, they've seen effects strikingly similar to Hawking radiation and even signs of black hole lasing behavior. These experimental analogs are incredibly important. Since we can't stick a thermometer into a real black hole or measure what's happening just beyond its event horizon, these models allow us to test and refine our theories. And what they're beginning to show is that the vacuum around a black hole may not be empty at all. It may be a seething, dynamic arena filled with quantum possibilities, where exotic radiation effects, including lasing, can occur naturally under the right conditions. In the case of a rotating black hole, or curved black hole, the effect becomes even more pronounced. The rotation drags spacetime around with it in a process called frame dragging, which leads to an ergosphere, a region outside the event horizon where nothing can remain still. It's in this ergosphere that negative energy states can exist, and where energy extraction becomes possible through processes like the Penrose process. These same principles underlie the idea of superradiance, and by extension, black hole lasing. Imagine a particle wave caught in the ergosphere, bouncing between gravitational boundaries, gaining energy with each pass. The energy doesn't come from nowhere, it's siphoned from the rotational energy of the black hole itself. Over time, this leads to a runaway effect, a burst of radiation that could, in theory, be detectable. In the most extreme version of this scenario, the amplification could be so intense that it destabilizes the black hole, leading to dramatic astrophysical phenomena we have yet to observe. But there's another layer to this story. Black hole lasers don't just challenge our understanding of astrophysics. They challenge the very foundations of how information and energy behave in curved spacetime. The fact that coherent radiation might emerge from a black hole-like region implies a level of order and structure to what we usually think of as the most chaotic and unknowable corners of the universe. It touches on the fundamental question: what happens to information that falls into a black hole? If black hole lasers can encode information in their radiation, perhaps through the coherent nature of the amplified waves, then they may hold the key to resolving the black hole information paradox, one of the deepest unsolved mysteries in physics. That's speculative, of course, but not impossible. In physics, especially at the frontier between quantum mechanics and gravity, speculation is often the first step toward discovery. There's also a fascinating relationship between black hole lasers and entropy. In thermodynamics, entropy is a measure of disorder, and black holes are known to have entropy proportional to their surface area, a bizarre but well-established fact from the laws of black hole thermodynamics. If lasing introduces coherence into the system, then how does that affect the entropy of the black hole? Does the emergence of structured radiation imply a decrease in internal disorder, or does it reveal a deeper structure within black hole thermodynamics that we have yet to comprehend? Even more intriguingly, could black hole lasers have cosmological implications? Could they have played a role in the early universe, where black holes might have formed rapidly amid the chaos of the Big Bang? If small primordial black holes existed, and if they could laze, then perhaps they seeded bursts of high-energy radiation in the early cosmos that left subtle imprints on the cosmic microwave background, or influenced structure formation in ways we've yet to detect. Of course, all of this hinges on the deepest layers of physics, layers we still don't fully understand. Quantum gravity, the elusive theory that will unite general relativity and quantum mechanics, might one day provide a clearer framework for understanding how black hole lasers fit into the grand tapestry of the universe. Until then, the idea remains speculative, but incredibly rich with possibility. Unlike the simplest Schwarzschild black holes, which are non-rotating and electrically neutral, rotating black holes, known as Kerr black holes, and charged black holes, known as Reissner-Nordstrom black holes, possess more complex structures. These black holes don't just have a single event horizon. They have multiple horizons, an outer event horizon and an inner horizon. The region between these horizons opens up new possibilities for wave behavior. In particular, the space between the inner and outer horizons can act like a resonant cavity, very similar in concept to the interior of a laser. Waves trapped in this cavity can reflect between the two horizons. One of the most fascinating outcomes is that under the right quantum conditions, these waves don't just bounce, they grow stronger. The trapped radiation is repeatedly amplified, leading to an instability. If this were a lab-based experiment, it would result in a beam of light being emitted. In the case of a black hole laser, it could lead to an outpouring of energy from the black hole system. Now, let's bring in the concept of superradiance. This is another crucial piece of the puzzle. Superradiance is a process by which waves, such as electromagnetic or scalar fields, can extract energy from a rotating black hole. If a wave enters the ergosphere, the region outside the event horizon where spacetime is dragged around by the black hole's rotation, it can be scattered in such a way that it emerges with more energy than it had before. The black hole loses a bit of its rotational energy, and the wave is amplified. Superradiance has been considered a kind of natural amplifier, a cosmic version of stimulated emission. Combine this with the concept of a wave bouncing back and forth between horizons, and you get something that behaves very much like a laser, a naturally occurring, gravitationally powered system that boosts radiation using the geometry of spacetime itself. This raises a startling question. If black hole lasers can theoretically exist, what would their output look like? Would they shine across the universe like stellar beacons? Would we be able to detect them? Or are they purely quantum mechanical, whispering only in the language of subtle radiation that's nearly impossible to hear? Theoretical models suggest that black hole lasers might not emit the kind of sharp, coherent beams of visible light that we associate with laboratory lasers. Instead, their emissions could manifest as bursts of exotic particles, energy pulses, or alterations in the quantum vacuum itself. In the context of analog gravity experiments, Scientists have even tried to simulate black hole lasers using systems of ultracold atoms or Bose-Einstein condensates, states of matter where quantum effects occur on a macroscopic scale. These laboratory analogs allow researchers to mimic the behavior of quantum fields in curved spacetime, offering a glimpse into how black hole lasers might function in the real universe. In fact, several analog experiments have already demonstrated phenomena consistent with black hole laser behavior. For example, using a flowing condensate of atoms, physicists have created configurations with horizons that trap sound like waves, phonons, and observed amplified echoes that match predictions of the black hole laser model. These aren't true black holes, of course, but they provide crucial experimental insight into a phenomenon that might otherwise remain entirely theoretical. What's especially intriguing is that these systems not only demonstrate amplification, but sometimes instability. The trapped waves don't just grow, they grow uncontrollably, eventually leading to a collapse or transformation of the system. This instability mirrors what theorists predict would happen near an actual black hole laser, where the amplification of quantum fields could destabilize the space between horizons, releasing bursts of energy. If such events occur in astrophysical black holes, they might help explain certain high-energy phenomena we observe but don't fully understand, like mysterious gamma-ray bursts or fast radio bursts. Could some of these sudden cosmic flashes be signals from black hole lasers at work? We don't yet know, but the possibility opens an incredible door. It suggests that black holes are not just endpoints of matter, not just cold, dark remnants of stellar collapse, but dynamic engines of quantum activity, perhaps even the universe's most extreme information processors. They might encode, amplify, and eventually release data about the quantum vacuum, acting as cosmic-scale amplifiers of information. What's even more profound is that black hole lasers sit at the intersection of general relativity, quantum field theory, and thermodynamics, the three pillars of modern physics. They bring into focus some of the biggest open questions in science. How does gravity behave at quantum scales? What happens inside a black hole? Is information really lost when something falls in? Could amplified quantum radiation be a way for the universe to maintain balance, allowing black holes to broadcast clues about their contents? Physicists are still working through the math. The models are dense, the predictions subtle, but the implications are vast. And as we continue probing the frontiers of physics with more powerful telescopes, more refined detectors, and more sensitive quantum experiments, we may someday gather the evidence we need to prove, beyond theory, that black hole lasers are real. This setup, where superradiant waves are trapped and continuously amplified, forms the foundation of what theoretical physicists describe as a black hole laser. The idea builds on the concept of a black hole bomb, but the difference lies in stability. A black hole bomb refers to a theoretical scenario where the energy of trapped waves grows exponentially until the system becomes unstable and collapses. On the other hand, a black hole laser, in a more stable configuration, would maintain this energy amplification, essentially acting as an amplifier of radiation without leading to runaway collapse. In the theoretical world, these two scenarios often blur. But the black hole laser concept hints at a profound and exciting possibility, a stable, self-sustaining process in which a black hole, by interacting with quantum fields, could become a cosmic laser, emitting coherent, highly energetic radiation. It's almost as if a black hole could not only store information, like many theoretical models suggest, but also actively process and amplify that information into detectable energy outputs. This insight opens up more than just questions about black holes themselves. It challenges the conventional understanding of how energy and information are exchanged in extreme gravitational fields. In classical mechanics, we imagine energy as a quantity that is conserved. However, when you factor in the dynamics of black holes and quantum effects, things get far less straightforward. Could black hole lasers hold the key to a deeper understanding of the cosmos, where information is not lost inside black holes but is instead emitted in a highly controlled, highly energetic form? For now, these remain theoretical constructs, and our understanding of the practicalities behind black hole lasers is still being explored. But this does not mean we are far from tangible answers. In fact, experiments are already underway to probe these exact phenomena in more controllable settings. Analog black holes, which simulate the behavior of actual black holes using systems like fluid dynamics or Bose-Einstein condensates, are crucial in this pursuit. These systems replicate the critical features of black holes, like event horizons and the trapping of waves, without the need for an actual black hole. While these are not black holes in the strictest sense, they give us a way to study wave behavior, energy extraction, and superradiance in a laboratory environment. The hope is that these models will help refine our understanding of black hole lasers and possibly even guide us toward detecting real-world counterparts in space. Another avenue of inquiry is the potential connection between black hole lasers and some of the most mysterious astrophysical phenomena we observe. High-energy bursts of radiation, such as gamma-ray bursts and fast radio bursts, are some of the most energetic and puzzling events in the universe. Could these be the result of black hole lasers in action? Could the energy released by these cosmic events be amplified radiation from a black hole's interaction with quantum fields, emitted from the region between event horizons or through the ergosphere? The idea is tantalizing. If we could pinpoint the source of such energy emissions, it would not only help us understand black holes better but also give us a new way to study the quantum nature of spacetime itself. Understanding black hole lasers may unlock a new realm of possibilities, where the most enigmatic objects in the universe could be harnessing the very fabric of spacetime for energy amplification. In essence, black hole lasers could hold the key to unlocking more fundamental aspects of physics, pushing us ever closer to the elusive theory of quantum gravity. However, as much as we theorize, it's important to keep in mind that black hole lasers, like many aspects of quantum mechanics and general relativity, remain in the realm of theoretical exploration. We don't yet have the technology or observational tools to definitively confirm their existence. Observing them directly would require detecting incredibly faint emissions, energy signals so weak and distant that they might elude current telescopic capabilities. Yet, as advancements in observational technology continue, new tools may one day allow us to gather the necessary evidence. Instruments like the Event Horizon Telescope, which captured the first image of a black hole, are pushing the boundaries of what we can see in the cosmos. Perhaps, in the future, we'll not only observe black holes but also detect the unique signatures of their laser-like emissions. Moreover, this brings us to the broader implications of black hole lasers. If such phenomena exist, they could help resolve some of the long-standing mysteries surrounding black holes. For instance, how does information behave when it enters a black hole? The idea of black hole lasers could provide insights into whether information is truly lost or whether it can be encoded and emitted in a different form. These questions, tied deeply to the famous black hole information paradox, could be influenced by new theories that incorporate quantum mechanics and general relativity in ways we are only beginning to understand. For now, though, we're left with tantalizing glimpses. Theoretical models, analog experiments, and indirect evidence suggest that black hole lasers could be a real phenomenon. Whether or not they exist remains to be seen, but one thing is certain: the quest to understand black holes continues to push the boundaries of human knowledge, bringing us closer to unraveling the deepest secrets of the universe. The search for black hole lasers is not only a journey into the mysteries of astrophysics, but also a philosophical inquiry into the nature of the universe itself. If black hole lasers do exist, they might alter how we think about the most extreme environments in the cosmos. A black hole, often seen as an inescapable prison for matter and information, could instead be a source of powerful, energetic radiation, suggesting a deeper, more dynamic role for these cosmic giants than previously thought. One of the most profound aspects of this exploration is the link between black hole lasers and the famous holographic principle. The holographic principle proposes that all the information contained within a volume of space can be represented on the boundary of that space. This radical idea, which comes from the study of black holes and quantum gravity, suggests that information inside a black hole might not be lost after all. Instead, it could be encoded in subtle ways, possibly through the radiation emitted by a black hole laser. This raises another exciting question: could black hole lasers serve as the mechanism through which this encoded information is released back into the universe? As we've already seen, black holes are often portrayed as information sinks, places where everything that enters is irretrievably lost. However, if black hole lasers are real, it might be that the information isn't lost after all. Instead, it could be amplified and released in a highly controlled form, like an extremely powerful cosmic laser. This concept could help resolve the black hole information paradox, which is one of the most puzzling aspects of modern physics. At the heart of this paradox is the tension between general relativity and quantum mechanics. General relativity describes the gravitational behavior of large-scale objects like black holes, while quantum mechanics governs the tiny, subatomic world. These two frameworks are remarkably successful within their domains, but they clash when trying to describe the singularity inside a black hole, where both extreme gravity and quantum effects are at play. The black hole laser hypothesis might offer a bridge between these two realms. It suggests that black holes, rather than being ultimate information destroyers, could be active players in the universe's information exchange network. The idea of information being emitted from a black hole via a laser-like process would not only reshape our understanding of black holes but also offer a new perspective on the nature of the universe itself. It suggests that even in the most extreme environments, the universe might be capable of intricate, delicate processes that we are only beginning to comprehend. But black hole lasers also present a series of challenges for both theorists and observational astronomers. For one, as previously mentioned, detecting emissions from black hole lasers would be an immense task. Black holes are, by their very nature, invisible to traditional observation methods because they trap light and other forms of radiation within their event horizons. This means that any emission from a black hole, even a laser-like one, would likely be incredibly faint and hard to detect from vast distances. Moreover, such emissions could be deeply masked by other sources of radiation in the universe, such as stars, supernovae, and the general cosmic microwave background. This is where the study of analog black holes becomes invaluable. In laboratories here on Earth, researchers have been able to simulate the behavior of black holes using various systems, such as fluid dynamics or ultracold quantum gases. By creating a setup where waves behave similarly to those near an actual black hole, scientists can test out the predictions of black hole lasers without needing to directly observe a real black hole. These experiments have already shown that wave amplification and superradiance-like effects can occur in controlled environments. As these analog experiments become more sophisticated, they might help bridge the gap between theory and real-world detection. In the realm of observational astronomy, future telescopes and space-based observatories will play a critical role in the search for black hole laser signals. Instruments that can detect high-energy radiation across various wavelengths, ranging from X-rays to gamma rays, will be essential. Missions like the James Webb Space Telescope, which is designed to observe infrared wavelengths, and the upcoming Square Kilometre Array, which aims to study radio waves in unprecedented detail, may one day reveal the faint whispers of black hole lasers. The hunt for black hole lasers could also dovetail with the search for other exotic cosmic phenomena, such as Hawking radiation. While black hole lasers are a highly specific prediction, they share some common ground with the idea of Hawking radiation, which posits that black holes should emit a faint glow due to quantum effects near the event horizon. Hawking radiation is incredibly weak and difficult to detect, but it presents another way in which black holes might not be the empty, silent voids we once thought. Instead, they could be dynamic entities, releasing subtle but powerful forms of energy. The implications of these discoveries extend far beyond black hole physics. If we confirm the existence of black hole lasers, it could open up new avenues of research into quantum field theory, the nature of spacetime, and even the fundamental laws that govern our universe. It might also help in the development of new technologies, particularly in the field of energy production. The idea of amplifying energy in such an extreme way, powered by the gravitational field of a black hole, could have applications in future energy systems, albeit far beyond the capabilities of current technology. One exciting potential application could be in the realm of astrophysical propulsion. Imagine harnessing the energy of a black hole laser to power a spacecraft. The concept of using black hole energy for propulsion might sound like science fiction, but the mathematics behind these systems suggests it is not entirely out of reach. A black hole laser could, in theory, be used to create a concentrated beam of energy that might be directed to power advanced spacecraft, providing propulsion for interstellar missions. However, before any of these possibilities can be realized, much work remains to be done. There are many unknowns, particularly when it comes to the quantum processes that govern black holes. Yet, the exploration of black hole lasers represents one of the most exciting frontiers in theoretical physics. It challenges our understanding of what black holes are, what they do, and how they fit into the broader cosmic tapestry. As we push forward with new experiments, new telescopes, and new theoretical models, the mysteries of black hole lasers will continue to unfold, revealing new insights into the nature of the universe. As we continue our exploration of black hole lasers, we must delve deeper into the foundational concepts that underpin these phenomena, bridging the abstract theoretical frameworks with the tangible aspects of the universe. At the heart of black hole lasers is the interplay of extreme gravitational forces and quantum effects. It's not just about the black hole itself, it's the environment around it, the quantum fields, and the waves that interact in and around the event horizon. These interactions produce the distinctive features that we associate with black hole lasers, most notably, the amplification of radiation. One of the crucial aspects of this process is the concept of the ergosphere. This is the region around a rotating black hole, just outside the event horizon, where space-time itself is dragged in the direction of the black hole's spin. This effect is known as frame dragging, and it causes objects within the ergosphere to move in the direction of rotation, creating a dynamic environment ripe for energy extraction. In the context of a black hole laser, the ergosphere is where the superradiance effect happens. Superradiance occurs when a wave, whether it's electromagnetic, gravitational, or something else, interacts with the black hole's gravitational field in such a way that the wave is amplified. This can be seen as the wave's energy being borrowed from the black hole, causing the black hole to lose energy in exchange for the amplified wave. It's a fascinating exchange of energy, where the black hole is, in a sense, powered by the energy it emits. This energy extraction, however, doesn't come without consequence. The energy extracted from the black hole affects its rotation, and this connection is a crucial part of the theoretical underpinnings of black hole lasers. But how do these amplified waves lead to a coherent, laser-like emission? The key lies in the boundary conditions of the space around the black hole. In many models of black hole lasers, it's assumed that there's a mechanism, likely related to the interaction between the superradiant waves and certain quantum fields, that enables the continuous amplification of radiation. As these waves propagate outward from the black hole, they bounce off the boundary, either a hypothetical reflecting wall or, in the case of real black holes, the dynamics of the surrounding accretion disk or other cosmic features. This reflective boundary helps sustain the amplification process. This idea isn't purely theoretical. There are already known astrophysical systems that display some of the features we would expect from black hole lasers. For instance, certain types of pulsars, rapidly rotating neutron stars, can emit highly collimated beams of radiation that behave somewhat like a laser, though not as coherently as what we imagine for a black hole laser. Additionally, active galactic nuclei, which are powered by supermassive black holes at their centers, sometimes emit highly energetic jets of radiation. These jets, which are driven by the intense gravitational and magnetic fields of black holes, could theoretically contain elements of black hole laser-like behavior. However, even though we have some observational evidence that supports the idea of energy extraction from black holes, such as from quasars and gamma-ray bursts, we still do not have direct evidence of black hole lasers. This is largely because the energy signatures from a black hole laser would be incredibly faint and would require next-generation observatories to detect. Furthermore, detecting the exact nature of radiation coming from black holes is complicated by the presence of the accretion disk, which is a swirling mass of gas and matter that typically surrounds a black hole. The material in the accretion disk is heated to extreme temperatures as it spirals inward, emitting X-rays and other forms of high-energy radiation. Disentangling the emission from the black hole itself from the radiation produced by the accretion disk is a significant observational challenge. Yet, these difficulties have not deterred scientists. In fact, the growing field of gravitational wave astronomy offers new hope. Gravitational waves, which are ripples in space-time caused by massive objects like black holes and neutron stars, can provide an entirely new way to study black holes and their behavior. If black hole lasers exist, they might produce gravitational wave signals that could be detected by instruments like LIGO and Virgo. These waves could provide insights into the dynamics of black holes, including their rotational behavior and their interactions with the surrounding quantum fields. Theoretical models continue to evolve, and some suggest that black hole lasers might be a necessary component of the evolution of black holes in certain cosmic environments. For instance, in the early universe, the conditions around black holes were vastly different from what we observe today. High-energy radiation and the amplification of waves could have played a role in the formation and growth of the first supermassive black holes. If this is the case, black hole lasers might have been an integral part of the cosmic evolution of black holes, offering a new avenue for energy transfer in the very early universe. One thing is clear: the implications of discovering a black hole laser are far-reaching. Not only would it revolutionize our understanding of black holes and their role in the universe, but it could also provide valuable insights into the behavior of quantum fields in extreme conditions. Moreover, it might offer a glimpse into the mysterious relationship between space-time and the fundamental forces of nature. Yet, despite the promise, there's much we still don't understand. For example, we're still in the early stages of understanding how black holes interact with quantum fields. The connection between quantum mechanics and general relativity is still one of the most fundamental challenges in theoretical physics. In particular, the nature of quantum gravity, how gravity behaves at the quantum level, remains elusive. If black hole lasers exist, they could be a key piece of the puzzle, revealing how quantum fields and gravity can work together in these extreme environments. Another key question concerns the stability of the laser-like radiation. In theory, black holes could emit continuous radiation indefinitely if conditions are right. However, it's unclear whether the dynamics of the surrounding space-time would allow for the sustained, stable production of laser-like emissions over long periods. This would depend on many factors, including the mass and spin of the black hole, the nature of the surrounding quantum fields, and the presence of external boundaries that can reflect and amplify radiation. The potential for practical applications of black hole lasers, while speculative, is nonetheless fascinating. As we explore the feasibility of harnessing energy from black holes, we find ourselves in the realm of science fiction. Could we one day learn how to tap into the power of a black hole laser for energy production or propulsion? This may sound far-fetched, but history has shown that many of the greatest scientific breakthroughs often start with ideas that seem impossible at first. The theoretical exploration of black hole lasers could, in the future, lead to technological advancements that allow us to harness the most extreme sources of energy in the universe. For now, the quest to understand black hole lasers remains a work in progress. It's a testament to the resilience of scientific inquiry that even in the face of vast cosmic distances and mind-boggling complexity, humanity continues to push forward. Each new discovery, each new insight, brings us closer to understanding the fundamental workings of the universe. And as our tools and theories evolve, who knows what we might find next in the strange and mysterious world of black holes. As we continue to unravel the mysteries surrounding black hole lasers, it's important to shift our focus to the broader implications these phenomena could have on our understanding of the universe. When we talk about black hole lasers, we're not just discussing an abstract idea. We're exploring the very fabric of spacetime, the behavior of quantum fields under extreme conditions, and even the potential for future technologies that could harness these powerful cosmic forces. One area where black hole lasers could offer profound insight is in the field of quantum gravity. Quantum gravity is the theoretical framework that aims to reconcile general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which explains the behavior of particles at the smallest scales. These two theories have been incredibly successful in their respective domains, but they are fundamentally incompatible in their current forms. General relativity describes gravity as the curvature of space-time caused by massive objects, while quantum mechanics deals with the probabilistic behavior of particles at the subatomic level. Black hole lasers, in all their theoretical glory, sit at the intersection of these two fields. A black hole, with its intense gravitational pull and singularity at its center, provides a unique laboratory for testing the laws of physics under extreme conditions. The environment surrounding a black hole, especially within the event horizon and ergosphere, offers an unparalleled setting to study how quantum fields behave in the presence of immense gravitational forces. By studying black hole lasers, we could gain insights into how quantum mechanics and general relativity can coexist, potentially paving the way for a unified theory of quantum gravity. This is not just about understanding black holes themselves, but rather the underlying principles that govern the universe as a whole. Black hole lasers may provide a glimpse into the ways quantum fluctuations can interact with the gravitational field of a black hole, leading to the amplification of waves in the process we call superradiance. This interaction could, in turn, shed light on the more elusive aspects of quantum field theory, such as how quantum fields behave in curved spacetime. One particularly intriguing aspect of black hole lasers is their potential connection to the information paradox, one of the most puzzling problems in theoretical physics. The information paradox arises from the question of what happens to information when it falls into a black hole. According to the principles of quantum mechanics, information cannot be destroyed. However, classical physics tells us that once something crosses the event horizon of a black hole, it is lost forever. This creates a fundamental contradiction between the two theories. Could black hole lasers hold the key to resolving the information paradox? Some theorists have suggested that the radiation emitted from black holes, particularly in the form of Hawking radiation or superradiant waves, might carry information about the matter that has fallen into the black hole. If this is true, the radiation could be a way for the black hole to leak information about the material it has consumed, allowing us to recover some of the information that seemed lost. This theory is still speculative, but it's a tantalizing possibility that could shift our entire understanding of how information behaves in the quantum realm. As we dive deeper into the realm of black hole lasers, it becomes increasingly clear that their theoretical existence could revolutionize several branches of physics. For instance, the study of black hole lasers could provide a direct method for testing quantum field theory in extreme gravitational environments. This is particularly important for understanding phenomena such as vacuum fluctuations, quantum entanglement, and the nature of quantum fields in curved spacetime. The interaction between quantum fields and the gravitational pull of a black hole is a frontier of modern physics, one that could help bridge the gap between quantum mechanics and general relativity. Another exciting possibility is that black hole lasers could offer insights into the behavior of spacetime itself. The event horizon of a black hole marks the boundary between the known universe and the unknown, where the laws of physics as we know them break down. By studying how radiation behaves near this boundary, scientists could gain new perspectives on the fundamental nature of space and time. For example, does the fabric of spacetime behave differently near the event horizon? Could the interactions that occur there provide clues about the true structure of the universe? These are questions that black hole lasers might help answer. In addition to their theoretical significance, black hole lasers could also have practical implications for our understanding of astrophysical processes. Many of the most energetic phenomena in the universe, such as the jets emitted by quasars and gamma-ray bursts, are thought to be closely related to black holes. These phenomena could, in some cases, be driven by processes similar to those in black hole lasers. If we can better understand how radiation is amplified and emitted from black holes, we might be able to refine our models of these high-energy astrophysical events. Furthermore, black hole lasers could have technological implications that are still difficult to predict. While the idea of harnessing energy from a black hole may sound like something straight out of science fiction, the theoretical study of black hole lasers could lay the groundwork for future technologies. For example, the study of superradiance and radiation amplification could eventually lead to the development of novel energy sources or even new methods of propulsion that leverage the intense gravitational fields of black holes. It's important to note, however, that we are still far from being able to directly observe or manipulate black hole lasers. Our current technology is not capable of observing the kind of fine-grained interactions required to detect superradiance, or the subtle amplification of radiation near black holes. The closest we can get to studying black holes is through indirect observations, such as the detection of gravitational waves, the study of the radiation emitted by accretion disks, or the imaging of black holes themselves, like the famous Event Horizon Telescope image of the supermassive black hole in the center of the M87 galaxy. Yet, as we continue to develop new technologies and observational techniques, we may one day have the tools to observe black hole lasers in action. The ongoing development of gravitational wave observatories, such as LIGO and Virgo, offers a new way to probe the most extreme environments in the universe. These instruments are capable of detecting the subtle ripples in spacetime caused by the collision of massive objects, such as black holes. If black hole lasers do exist, they could produce gravitational wave signals that are detectable by these observatories, providing us with another window into the behavior of black holes. In the coming decades, advances in both observational astronomy and theoretical physics may allow us to answer many of the outstanding questions surrounding black hole lasers. As we continue to probe the universe's most extreme environments, we will undoubtedly make new discoveries that challenge our understanding of the laws of physics and push the boundaries of what is possible. In the meantime, the study of black hole lasers remains one of the most intriguing and exciting areas of research in modern physics. Whether or not they exist, the pursuit of this phenomenon will likely lead to new breakthroughs in our understanding of quantum mechanics, general relativity, and the very nature of the cosmos. The search for black hole lasers may one day reveal deep truths about the universe that we can only imagine today, shaping the future of scientific exploration for generations to come. As the exploration of black hole lasers continues to expand, we must consider the potential ripple effects that these discoveries could have on other fields of science. The vastness of black holes' influence on their surroundings and the complexity of the phenomena they generate suggest that understanding black hole lasers could transform not just physics, but our fundamental perception of the universe. One key aspect of black hole lasers that could potentially revolutionize our understanding of physics is their relationship to the concepts of energy and entropy. The way energy is exchanged and conserved in extreme gravitational environments is a question that has baffled scientists for decades. In typical systems, energy flows through various mechanisms, such as electromagnetic radiation, kinetic energy, or potential energy. However, in the case of black holes, the rules are much murkier. The concept of energy conservation itself is tested to the extreme when dealing with objects whose gravitational pull is so intense that not even light can escape. This is where black hole lasers come into play. The superradiance effect, the theoretical mechanism behind black hole lasers, could hold critical insights into the relationship between energy, gravity, and the fate of matter within the event horizon. What happens to energy when it falls into a black hole? Does it truly disappear, or does it somehow survive, taking on a different form? The amplification of radiation in black hole lasers may provide the first direct evidence that energy isn't lost within a black hole, but rather, undergoes transformation in ways that we can only begin to understand. Entanglement, another core concept in quantum mechanics, could also find a unique testing ground in black hole lasers. Quantum entanglement refers to the phenomenon where particles become correlated in such a way that their states are interdependent, even when separated by vast distances. While this concept has been experimentally verified on small scales in laboratory settings, the extreme conditions near a black hole might offer an entirely new environment for studying entanglement on a cosmic scale. If black hole lasers do indeed amplify quantum fluctuations and interact with the surrounding spacetime, it is possible that the quantum entanglement between particles near the event horizon could be studied in ways that have never been possible before. As quantum entanglement and superradiance come together in the environment of a black hole, we are faced with new opportunities to explore the deepest questions in modern physics. Could black hole lasers be a window into the strange, often paradoxical behavior of quantum fields in curved spacetime? Could they help to clarify our understanding of quantum mechanics as applied to extreme gravitational environments, where the effects of both general relativity and quantum theory must be taken into account? These questions are not just theoretical musings. They are fundamental to the future of physics. The resolution of these paradoxes would have far-reaching implications, potentially uniting two of the most successful theories in science, quantum mechanics and general relativity. But before we can unlock the secrets of black hole lasers, we must develop new theoretical frameworks and advanced observational tools to test these concepts. Fortunately, the tools we need are slowly but surely becoming available. One of the most exciting developments in astrophysics is the advancement of gravitational wave observatories. Instruments such as LIGO and Virgo, which have already detected signals from the collision of black holes, could potentially be used to detect gravitational waves generated by black hole lasers. These waves would carry unique signatures of the interactions between quantum fields and the intense gravitational forces near the black hole's event horizon. By identifying these specific waveforms, scientists could not only confirm the existence of black hole lasers but also study the detailed dynamics of how radiation is amplified in such extreme environments. The next frontier in this field is the potential detection of gravitational waves from rotating black holes that exhibit superradiance. Theoretical models predict that under certain conditions, such as when a black hole spins rapidly and is surrounded by an accretion disk, the energy extracted from the black hole through superradiance could lead to the emission of detectable gravitational waves. These waves could carry critical information about the properties of the black hole, including its spin, mass, and the behavior of surrounding matter. The observation of these waves would be a game-changer in our understanding of black hole physics, offering us a direct observation of processes that occur at the very edge of space-time. As exciting as the potential for detection is, we must also consider the future role that black hole lasers could play in space exploration and technology. While harnessing energy from a black hole may sound like science fiction, the theoretical study of such processes could inspire new technological innovations. For instance, the principles of radiation amplification and energy extraction from black holes might one day be applied to the development of advanced propulsion systems for interstellar travel. Imagine spacecraft that can utilize the gravitational energy of a black hole to propel themselves at incredibly high speeds, potentially making interstellar travel a reality. Furthermore, black hole lasers could offer new ways to study the formation and evolution of galaxies. Supermassive black holes, found at the centers of most galaxies, are thought to play a central role in galaxy formation and evolution. Understanding the processes that occur around these black holes could help scientists better understand how galaxies evolve over cosmic timescales. By studying the radiation emitted by black holes, including any signatures of superradiance or other phenomena, we could gain new insights into the conditions that govern the growth and structure of galaxies. In addition to the cosmic implications, there may be practical applications for black hole lasers here on Earth. While harnessing energy from a black hole remains a far-off dream, the fundamental research into superradiance and quantum field theory could lead to breakthroughs in areas such as quantum computing, energy storage, and even the development of new materials with extraordinary properties. The theoretical study of black hole lasers could provide a new way of thinking about energy and quantum mechanics, potentially leading to innovations that we can't yet fully imagine. As we approach the frontiers of our understanding, it's important to remember that black hole lasers are still, for the most part, a theoretical concept. While the math and models suggest that they could exist, we still have a long way to go before we can observe them directly. However, the pursuit of understanding black hole lasers is more than just a scientific curiosity. It is a journey that could reshape our understanding of the universe, challenge our assumptions about the nature of space-time, and open up new frontiers in both physics and technology. The future of black hole laser research is bright. New observational tools, such as the James Webb Space Telescope, are opening up the cosmos to unprecedented levels of detail. At the same time, advancements in theoretical physics, such as the study of quantum gravity, are bringing us closer to understanding how quantum mechanics and general relativity can work together. These combined efforts will likely lead to the discovery of black hole lasers, offering us a new way to observe and interact with some of the most mysterious objects in the universe. In the coming decades, the exploration of black hole lasers may answer some of the most profound questions in science, from the nature of quantum fields to the behavior of energy and information in extreme environments. As we continue to explore these phenomena, we will undoubtedly push the boundaries of human knowledge, perhaps unlocking secrets that have been hidden for the entire history of the universe. With the growing interest and investment in space exploration, coupled with the rapid advancements in physics and technology, it's only a matter of time before black hole lasers transition from a theoretical curiosity to a central topic of study in modern physics. As we push the limits of our understanding, the study of these cosmic phenomena could one day lead to breakthroughs that will shape the future of science, technology, and our understanding of the very fabric of the universe. As we look to the future, it's crucial to recognize the importance of multidisciplinary approaches in unlocking the mysteries surrounding black hole lasers. While theoretical physicists and astronomers have laid the groundwork for understanding these phenomena, the discovery and study of black hole lasers will require collaboration across various fields. Astrophysics, quantum mechanics, general relativity, and computational physics will need to converge in ways that may currently seem impossible. The merging of these domains could lead to revolutionary new insights not only into the workings of black holes but into the fabric of the cosmos itself. One potential avenue for progress lies in the growing power of computational models. As the power of supercomputers continues to increase, so too does our ability to simulate the extreme environments around black holes with unprecedented accuracy. These simulations can allow scientists to test various hypotheses about black hole lasers, studying how they might behave in different scenarios, such as the presence of accretion disks, magnetic fields, or companion stars. By refining these models, researchers can generate predictions about the specific signatures we should look for in the cosmos. Moreover, with the growing sophistication of computational tools, it's becoming possible to simulate not just the physics of black holes themselves but the quantum fields that interact with them. This means that black hole lasers could soon be studied from a purely theoretical standpoint before any direct observational evidence is even available. The results of these simulations could guide the development of observational strategies, helping astronomers to focus their efforts on the most promising sources of black hole laser activity. In addition to computational advancements, experimental methods will also play a significant role. Although we can't yet directly observe black hole lasers, scientists are already developing techniques to probe the behavior of extreme gravitational fields in other contexts. One promising technique involves studying the behavior of matter in high-energy environments, such as those created in particle accelerators. The physics of black holes and the exotic phenomena that surround them could, in theory, be replicated on a smaller scale in controlled experiments. These experiments could provide insight into the behavior of superradiant amplification, energy extraction, and even the very properties of black holes themselves. However, perhaps the most promising developments are happening at the observational front. The next generation of telescopes and gravitational wave observatories are going to provide an unprecedented level of detail when it comes to observing black holes. Instruments like the Event Horizon Telescope, which recently captured the first image of a black hole's event horizon, will continue to push the boundaries of observational astronomy. In addition, upcoming space-based observatories such as the James Webb Space Telescope are set to offer high-resolution images and spectra of cosmic phenomena, including the radiation emitted from black holes. As these instruments continue to improve, they may provide us with the first concrete evidence of black hole lasers. Gravitational wave detectors, like LIGO and Virgo, are also making waves in the field of astrophysics. These detectors have already recorded signals from merging black holes and neutron stars. They can, in theory, detect gravitational waves produced by the kinds of interactions that occur near black holes, including those related to superradiance and the formation of black hole lasers. By analyzing these gravitational waves in greater detail, scientists can potentially detect the unique signatures of black hole laser activity. Even though direct observation of black hole lasers remains a challenge, there is a growing optimism in the scientific community that we are getting closer to a breakthrough. The next decade promises to be one of discovery, as these cutting-edge technologies and theoretical advancements continue to converge. As the ability to detect gravitational waves improves, and with the launch of more powerful telescopes, the first observation of black hole lasers may be just around the corner. These observations will be nothing short of revolutionary. The potential ramifications of black hole lasers, once confirmed, extend beyond simply confirming a new phenomenon in astrophysics. If the mechanisms behind these lasers can be understood and quantified, they could have implications for our understanding of the nature of light, energy, and the very structure of space-time. Black holes, long considered some of the most enigmatic objects in the universe, could suddenly reveal themselves as powerful laboratories for testing some of the most fundamental questions in physics. Additionally, the study of black hole lasers may influence broader areas of scientific research. For example, cosmologists studying the evolution of galaxies may gain new insights into the interplay between supermassive black holes and their surrounding environments. Since black holes play such a central role in galaxy formation, understanding the energy dynamics at the core of these galaxies could unlock important clues about the universe's large-scale structure. Could black hole lasers be a key factor in the regulation of star formation or the evolution of galaxies over cosmic timescales? Even more speculative, but still intriguing, is the potential for practical applications. As we've seen in other areas of science, discoveries that initially appear purely theoretical can sometimes lead to groundbreaking technologies. The amplification of energy in a black hole laser, if understood and harnessed, could lead to new forms of energy production that are beyond anything we can currently imagine. While this may sound like science fiction, the fact is that some of the most transformative technologies in human history, such as the laser itself, began as theoretical concepts long before they were practically realized. In the realm of space exploration, black hole lasers might one day play a role in propelling spacecraft across vast distances. The extreme energy densities in the vicinity of a black hole could potentially be harnessed for propulsion or energy generation, allowing for more efficient long-distance travel across the cosmos. While this is still far beyond our current technological capabilities, the study of black hole lasers could provide the foundational understanding needed to develop these advanced propulsion systems. In a more immediate sense, the research into black hole lasers could also inspire the development of more efficient lasers and energy systems here on Earth. By understanding the processes of superradiance and radiation amplification in such extreme environments, we could apply similar principles to develop new technologies in telecommunications, quantum computing, and materials science. The phenomenon of black hole lasers, therefore, might inspire not just cosmic exploration, but also practical innovations that could revolutionize industries here on Earth. For now, the study of black hole lasers remains primarily theoretical, but as we continue to push the boundaries of what we know about the universe, we inch closer to understanding these cosmic phenomena in greater detail. The interplay between quantum mechanics, general relativity, and the extreme conditions around black holes presents one of the most exciting challenges in modern science. As we continue to refine our theoretical models and develop increasingly sophisticated observational tools, it seems likely that the mysterious world of black hole lasers will soon be within our grasp. The discovery and understanding of black hole lasers could serve as a landmark achievement in the history of science. It represents the intersection of our most advanced theories of physics and the uncharted territories of the cosmos. In the process, we may gain insights into the very nature of the universe itself, offering answers to some of the deepest questions that have puzzled humanity for centuries. As we venture further into this field, we are not just studying black holes, we are exploring the very fabric of reality. As we push the boundaries of our understanding, the implications of black hole lasers extend beyond the confines of just astrophysics and cosmology. The potential discoveries stemming from the study of these phenomena could ripple through multiple fields of scientific inquiry, influencing everything from quantum mechanics to the future of energy production. As scientists develop more sophisticated models, we may come to understand not only the mechanics behind black hole lasers but also their place within the broader framework of universal laws. One of the key aspects of black hole lasers that continues to intrigue researchers is the role of quantum mechanics in these extreme environments. Quantum theory, which governs the behavior of particles at the smallest scales, has long been a field of study in astrophysical contexts, but black holes provide a unique challenge. The interaction of quantum fields with the intense gravitational forces near a black hole could lead to some of the most extreme quantum phenomena ever observed. Superradiance, which underpins the concept of black hole lasers, is a direct result of the quantum mechanical properties of particles in strong gravitational fields. These quantum processes near black holes could also have far-reaching consequences for the development of quantum technologies on Earth. The study of quantum fields in the presence of extreme gravity could lead to the development of new quantum devices, such as ultrasensitive sensors capable of detecting incredibly small changes in gravitational fields. Black hole lasers, in essence, could provide us with the ultimate laboratory to explore the strange and often counterintuitive world of quantum mechanics in the most extreme conditions imaginable. Furthermore, the study of black hole lasers could revolutionize our understanding of light itself. Light behaves in ways that often defy our classical understanding of physics, especially in the intense environments near black holes. The process of superradiance in black hole lasers, for example, involves the amplification of light to such a degree that it may outshine the black hole itself. This behavior challenges our understanding of light's interaction with gravity, and could provide clues about how light interacts with the fabric of spacetime. If black hole lasers can be studied in greater detail, we may be able to answer long-standing questions about the nature of light and its relationship to the fabric of the universe. On a more practical level, the insights gained from black hole lasers could also inspire new approaches to energy production. Currently, humanity is in search of cleaner, more efficient sources of energy to meet the growing demands of an ever-expanding population. One of the greatest challenges facing humanity is the creation of sustainable energy sources that can power our civilization without further damaging the planet. Although harnessing the energy of a black hole remains firmly in the realm of science fiction, the principles underlying black hole lasers could one day inform more practical solutions. For example, understanding how energy can be extracted from extreme environments could provide inspiration for new types of energy sources here on Earth, potentially leading to breakthroughs in energy harvesting technologies. The study of black hole lasers may also impact other scientific fields that deal with high-energy phenomena, such as plasma physics and magnetohydrodynamics, MHD. In the extreme gravitational fields near black holes, matter behaves in ways that differ greatly from how we typically observe it. The interaction of magnetic fields, plasma, and gravity in these regions could offer new insights into the fundamental processes that govern the behavior of matter under extreme conditions. Researchers in the field of plasma physics have long been interested in understanding how plasma behaves in high-energy environments, and black hole lasers could offer a unique opportunity to study these processes in the most extreme conditions. In addition, the study of black hole lasers could lead to breakthroughs in the field of gravitational wave astronomy. While much of the focus in gravitational wave research has been on detecting signals from black hole mergers or neutron-star collisions, black hole lasers could provide an entirely new avenue for observation. The amplification of energy near a black hole could generate gravitational waves in addition to the electromagnetic radiation produced by these processes. By analyzing the gravitational wave signals produced by black hole lasers, scientists could gain new insights into the nature of black holes, the interactions between quantum fields and gravity, and even the fundamental properties of spacetime itself. The potential for black hole lasers to provide new ways to probe the universe is immense. For instance, if we can detect the unique signals emitted by black hole lasers, we might be able to gain a clearer understanding of the behavior of matter and energy under extreme conditions. This could have profound implications for our understanding of the formation and evolution of black holes, as well as their role in the larger context of galaxy formation and cosmic evolution. Studying the emissions from black hole lasers could also shed light on the distribution of dark matter and dark energy, two of the most mysterious and elusive components of the universe. In a broader sense, the quest to understand black hole lasers is also part of humanity's larger search for meaning in the cosmos. Throughout history, humans have gazed up at the stars, seeking to understand the forces that shape the universe and our place within it. The study of black hole lasers, along with other mysterious cosmic phenomena, allows us to explore some of the most fundamental questions in science. What are the limits of our understanding? How do the most extreme conditions in the universe shape the laws of physics? And perhaps most importantly, how does the study of the universe at its most extreme help us understand the fundamental nature of reality? As researchers continue to probe the mysteries of black hole lasers, it's clear that we are on the verge of major scientific breakthroughs. Theoretical models, computational simulations, and cutting-edge observational technologies are all converging to make the study of black holes and their exotic phenomena more achievable than ever before. While the direct observation of black hole lasers remains a distant goal, the pursuit of this phenomenon will undoubtedly yield valuable insights into the very nature of space, time, and energy. In the coming years, it's likely that the study of black hole lasers will spark new discoveries not only in astrophysics, but across many other fields of science. Whether it's advancing our understanding of quantum mechanics, providing new insights into the behavior of light and matter, or inspiring breakthroughs in energy production, the exploration of black hole lasers promises to push the limits of human knowledge in exciting and unexpected ways. As scientists continue to explore these cosmic wonders, they may uncover answers to some of the deepest questions about the universe and the fundamental forces that govern it. So, as we look toward the future of black hole laser research, we can only imagine the possibilities that await. Each new discovery brings us closer to understanding these mysterious cosmic phenomena, and as we expand our knowledge, we may find that black hole lasers are not only fascinating phenomena but crucial pieces in the grand puzzle of the universe. Whether it's exploring the fundamental nature of light, energy, or gravity, or applying these insights to practical technologies here on Earth, the study of black hole lasers is sure to play a central role in the next wave of scientific breakthroughs. As the study of black hole lasers progresses, it's important to emphasize the broader implications that these phenomena might have on the way we perceive the universe. In the grand scheme, black holes themselves are already enigmatic objects, acting as the ultimate testbed for some of the most intense and extreme conditions in the cosmos. The possibility that they could emit amplified light or radiation in the form of black hole lasers only adds another layer of mystery to these celestial behemoths. At the heart of the fascination with black hole lasers lies the relationship between light, gravity, and energy. In the context of these supercharged phenomena, we begin to observe how the gravitational forces near a black hole can profoundly influence light. The process of superradiance, central to the idea of black hole lasers, challenges our intuition about how light interacts with gravity. Instead of being absorbed, as it is by most objects in the universe, light is amplified near black holes in a way that mirrors the operation of a laser. This defies our classical understanding of gravity, as black holes are traditionally thought to trap everything, even light, once it crosses the event horizon. The gravitational pull near black holes is so intense that it bends the path of light and time itself. But as black hole lasers suggest, this intense gravity might be harnessed in unique ways that open new avenues for understanding the interaction of energy and gravity. It's this unique ability to warp space and time that makes black holes such powerful sources of curiosity and investigation. These extreme environments are so far removed from what we experience on Earth that every new discovery, such as the potential for black hole lasers, feels like uncovering an entirely new realm of physics. On a quantum level, the amplification of energy through superradiance and black hole lasers touches on the very essence of how quantum fields behave. Quantum fields are fundamental to our understanding of the universe, as they provide the backdrop against which all matter and energy interact. In the case of black hole lasers, it's the interaction between quantum fields and the gravitational forces near a black hole that leads to the creation of such an intense energy outflow. These quantum processes, which are influenced by the curvature of spacetime, challenge classical ideas about how energy is conserved and distributed. One of the most promising aspects of the study of black hole lasers is how it could impact our understanding of the vacuum state of quantum fields. In quantum mechanics, the vacuum is not empty space as we might imagine, but a seething, dynamic environment where particles constantly pop in and out of existence. The study of black holes, particularly black hole lasers, could offer a new perspective on the nature of this vacuum. The behavior of quantum fields in the presence of extreme gravity could shed light on the nature of these fleeting, ephemeral particles, and perhaps even uncover new states of matter or energy that we haven't yet encountered. Furthermore, these findings could play a pivotal role in the ongoing search for a unified theory of everything. A central goal of modern physics is to reconcile the two pillars of the field: general relativity, which describes the gravitational forces governing the cosmos, and quantum mechanics, which governs the behavior of particles on the smallest scales. Black hole lasers, which sit at the intersection of these two realms, might offer crucial insights into how these two theories can be reconciled. By studying how quantum fields behave in the extreme environment of a black hole, researchers might be able to uncover new ways to combine the principles of general relativity and quantum theory, bringing us one step closer to a unified theory. The potential applications of this research extend beyond theoretical physics. The knowledge gained from studying black hole lasers could have far-reaching consequences in fields ranging from energy production to the development of new technologies. As our ability to understand and manipulate quantum processes improves, we may find new ways to harness these processes for practical purposes. For example, quantum lasers, which are based on the principles of quantum mechanics, already hold promise for a range of applications in areas like telecommunications and computing. By gaining a deeper understanding of how light behaves near black holes, scientists could unlock new methods for generating and controlling light in ways that were previously unimaginable. Another area where black hole lasers could have a profound impact is in the realm of space exploration. If the phenomena associated with black hole lasers can be understood and controlled, they could potentially serve as a new tool for studying the most distant regions of the universe. The intense radiation emitted by black hole lasers could be used to probe the properties of distant galaxies, helping scientists to measure the distribution of matter and energy across the cosmos. This could provide valuable insights into the evolution of the universe and the forces that shape its large-scale structure. Black hole lasers could also have applications in the development of space propulsion systems. In principle, the energy emitted by a black hole laser could be harnessed to propel spacecraft at speeds far greater than what is possible with conventional propulsion methods. By tapping into the immense energy present in the vicinity of black holes, we might be able to develop new forms of propulsion that could revolutionize space travel. While this is still far beyond our current technological capabilities, the mere possibility that black hole lasers could be harnessed for such purposes illustrates the incredible potential of this phenomenon. As we delve deeper into the study of black hole lasers, we may also find that they are part of a broader family of phenomena related to superradiance and quantum field behavior in extreme gravitational environments. Just as black holes themselves represent the limits of our understanding of space and time, black hole lasers could serve as a key to unlocking even more mysteries about the fundamental nature of the universe. Whether through new insights into quantum mechanics, breakthroughs in energy production, or advancements in space exploration, black hole lasers are poised to play a pivotal role in the future of science and technology. The study of black hole lasers, in essence, invites us to push the boundaries of our imagination and to question everything we think we know about the universe. Every discovery, every new insight, brings us closer to understanding the true nature of the cosmos and our place within it. It's a journey that promises to challenge our most fundamental ideas and reshape our understanding of reality itself. As the research into these mysterious phenomena continues, we can only wonder what future revelations await, and how they will ultimately change the course of human knowledge. As we continue to explore the intricacies of black hole lasers, the theoretical underpinnings grow even more fascinating. One key factor in this ongoing research is the nature of the event horizon, the boundary beyond which nothing, not even light, can escape the pull of a black hole. It's this very property that has made black holes the subject of so much intrigue for decades. The notion that something as powerful as light could somehow escape or be amplified near a black hole challenges long-standing ideas and poses exciting questions about the fundamental workings of physics. The event horizon represents a crucial boundary in the study of black holes. It's the point of no return, where the gravitational pull becomes so strong that not even light, traveling at its fastest possible speed, can escape. This characteristic has led to the belief that black holes are truly black, and that nothing can escape from them once it's past the horizon. However, the concept of black hole lasers upends this understanding by suggesting that, under certain conditions, the energy that once would have been trapped within a black hole can instead be directed outward, producing an amplified, highly focused beam of radiation. The mechanism that could allow such an extraordinary event to happen is still theoretical but is grounded in the physics of superradiance. This phenomenon occurs when waves, such as light or other forms of electromagnetic radiation, interact with a rotating black hole. In these circumstances, the waves can gain energy from the black hole's rotation, resulting in the amplification of the wave's intensity. This is where the idea of black hole lasers begins to take shape, a process where the gravitational pull of the black hole essentially squeezes the energy of the waves, causing them to grow in strength rather than being pulled into the black hole. However, the conditions necessary for a black hole laser to form are incredibly specific. First, the black hole must be rotating. A non-rotating, or Schwarzschild black hole, doesn't possess the necessary angular momentum to facilitate superradiance. It's only when the black hole is spinning rapidly that the conditions for superradiance are met, making it a key feature for the existence of black hole lasers. Secondly, the surrounding environment plays a significant role. For black hole lasers to truly form, the medium around the black hole must be dense enough to allow the waves to interact with the black hole's gravitational field. Without the right conditions, such as a cloud of particles or an accretion disk surrounding the black hole, the energy necessary for superradiance may never build up to the point where it becomes a visible, detectable phenomenon. The discovery of black hole lasers, if confirmed, could lead to a breakthrough in our understanding of energy, quantum fields, and gravity. It would mark a dramatic shift in how we think about the relationship between light and gravity. If gravitational fields can be used to amplify electromagnetic radiation, it might mean that similar processes could be harnessed in other extreme conditions throughout the universe. The study of black holes has already revealed that gravity has some very strange effects, such as time dilation and space curvature, but the possibility that it could also be used to produce focused, amplified light could revolutionize our understanding of the universe in ways we cannot yet fully comprehend. One area that could benefit from the study of black hole lasers is astrophysics. If we can develop the tools to detect these types of radiation emissions from distant black holes, it could provide us with new ways of observing these mysterious objects. Currently, black holes are studied primarily through the observation of their effect on nearby matter, such as stars and gas clouds, or through the detection of gravitational waves from black hole mergers. But the detection of black hole laser-like emissions would offer a new avenue for exploration. It could provide insights into the rotational dynamics of black holes, the behavior of matter in the event horizon's proximity, and even the mysterious physics of the singularity, the core of the black hole where densities and gravitational forces become infinitely strong. Furthermore, understanding black hole lasers could also have implications for the broader study of high-energy physics. The energy released in such phenomena would be massive, and studying how this energy is concentrated and amplified could help scientists create new models for energy production or energy transfer on an unimaginable scale. These discoveries might lead to the development of new technologies that use the principles behind black hole lasers to produce more efficient energy sources or to create methods of controlling and utilizing extreme energies in other fields. Looking ahead, black hole lasers could even inform the development of next-generation space exploration tools. If scientists can develop a deep understanding of how these lasers operate, they may be able to design devices capable of harnessing the extreme energies of black hole radiation for propulsion or energy generation in deep space. The use of such technology would completely redefine space travel as we know it, potentially making interstellar travel a possibility within the distant future. As fascinating as the potential applications may be, the theoretical study of black hole lasers is still in its infancy. While much progress has been made, and the idea has been explored in various scientific papers and theoretical models, confirming the existence of black hole lasers in the real universe will require significant advances in technology. We must develop better observational tools that are capable of detecting the subtle radiation produced by black holes in these extreme environments. With current technology, capturing such faint signals is difficult, but advancements in both space-based telescopes and theoretical physics could provide the breakthroughs needed to confirm these phenomena. The possibility of black hole lasers also ties into broader, fundamental questions in physics. For example, the study of black holes and the search for phenomena like black hole lasers force us to confront the limitations of our current models of the universe. We are constantly challenging our understanding of the fundamental forces of nature, gravity, electromagnetism, the strong force, and the weak force, and black hole lasers, by offering a new way to think about gravity and light, may help us unlock new insights about these forces. Another avenue of exploration that might emerge from black hole laser studies is the potential role of quantum information. In recent years, quantum computing has gained significant attention, with its promise to revolutionize the way we process information. Could quantum information theory be used to understand the behavior of superradiance near black holes? What could black hole lasers teach us about the transfer of quantum information across space and time? These questions remain unanswered but could lead to significant breakthroughs in our understanding of both quantum mechanics and general relativity. Black hole lasers, though still a theoretical phenomenon, represent an exciting frontier in our understanding of the universe. They bridge the gap between some of the most extreme phenomena in the cosmos, blending quantum mechanics, general relativity, and the fascinating properties of black holes. Whether or not these laser-like emissions are confirmed in the future, the very idea of their existence is already challenging our notions of space, time, and energy, pushing the boundaries of what we know and inviting new discoveries that could change the course of science for generations to come. The research into these enigmatic objects will continue to evolve, pushing us toward a deeper understanding of the cosmos. As we explore the mysteries of black hole lasers, we are not only unlocking the secrets of black holes themselves but also advancing our knowledge of the universe at large. And in the process, we might just discover new principles of physics, new technologies, and new ways to interact with the universe that could transform human civilization forever. The search for understanding black hole lasers is, in many ways, a journey into uncharted territory. As we continue to explore this theoretical phenomenon, it's important to acknowledge the deep connections it shares with other complex and paradoxical phenomena in the universe. The intersection of general relativity and quantum mechanics, for example, has been a major focus of research in recent years. Black holes, as regions where these two forces clash, present a unique environment to explore the limits of both. One of the key challenges in confirming the existence of black hole lasers is the need for a deeper understanding of the behavior of light and matter near the event horizon. The event horizon of a black hole is an incredibly dynamic environment. It's the threshold beyond which anything, including light, cannot escape. However, due to the peculiarities of quantum mechanics, particularly the concepts of Hawking radiation and the Casimir effect, we know that the vacuum near the event horizon isn't entirely empty. It's filled with quantum fluctuations, brief and fleeting particles that appear and vanish at the quantum level. These quantum fluctuations play a crucial role in the theoretical concept of black hole lasers. They interact with the strong gravitational field near a black hole's event horizon, which can result in a process known as Hawking radiation, named after physicist Stephen Hawking. While Hawking radiation itself doesn't directly form a laser, it serves as a stepping stone toward understanding how energy behaves near black holes and could potentially inform the development of black hole lasers. Hawking radiation occurs when virtual particle pairs are created near the event horizon. Normally, these pairs annihilate each other quickly, but in the intense gravitational field near a black hole, one of the particles may be pulled into the black hole while the other escapes. The particle that escapes is what we call Hawking radiation. It's a quantum mechanical process that, in theory, could lead to the gradual evaporation of a black hole over time. The study of Hawking radiation is ongoing, and understanding how it works could offer critical insights into the creation of black hole lasers. The intriguing possibility of Hawking radiation also ties in with the idea of black hole evaporation. If we consider how energy behaves in this environment, we might find that black hole lasers could be linked to a process that extracts energy from the black hole's gravitational field in a controlled way. This process could, in essence, function as an energy amplifier, using the black hole's rotation and mass to convert gravitational energy into electromagnetic radiation. Such a conversion mechanism would provide a new lens through which to study the interaction between different forms of energy in the cosmos. Moreover, the physics behind black hole lasers could potentially open up new avenues for understanding the energy dynamics of other extreme environments in the universe. For example, there are other astrophysical objects, such as neutron stars and magnetars, that exhibit extreme magnetic fields and energetic radiation. If black hole lasers can be theoretically realized, it could suggest that similar phenomena might occur in these environments as well. By studying these objects in greater detail, scientists could potentially uncover more about how energy behaves in extremely intense gravitational and magnetic fields. While the theoretical aspects of black hole lasers have garnered much attention, it's equally important to consider the practical challenges of observing them. Black holes, by their nature, are incredibly difficult to study. They cannot be seen directly because their gravitational pull prevents light from escaping. The only way to study black holes is by observing the effect they have on nearby matter. For example, when matter falls into a black hole, it heats up and emits radiation, forming an accretion disk. In addition to this, gravitational waves produced by the mergers of black holes have provided us with valuable data about their properties. However, black hole lasers, if they exist, would present an entirely different challenge. The energy released in the form of electromagnetic radiation near the event horizon of a black hole would likely be incredibly faint and difficult to detect. To observe such radiation, scientists would need to rely on incredibly sensitive instruments that can detect extremely weak signals. These might include advanced space-based telescopes, which are capable of detecting high-energy photons from distant cosmic objects. For example, the Event Horizon Telescope, which captured the first image of a black hole in 2019, could one day be used to observe the radiation associated with black hole lasers. One intriguing possibility is the use of gravitational lensing to study black hole lasers. Gravitational lensing occurs when the intense gravitational field of a black hole bends light passing near it, much like a magnifying glass. By studying the way light is bent around a black hole, scientists can gain valuable information about the black hole's properties, as well as the behavior of any radiation it emits. This could provide us with a new way of studying the theoretical emissions from black hole lasers, allowing us to observe them indirectly, even if they are too faint to detect directly. Furthermore, one of the most exciting aspects of black hole lasers is the potential for them to challenge our understanding of the nature of space and time itself. Black holes are already known to have extreme effects on both, and the concept of black hole lasers introduces an entirely new set of questions about the interplay between gravitational fields and electromagnetic radiation. Could the creation of black hole lasers somehow provide insight into the fundamental structure of space-time? Could they help us bridge the gap between general relativity, which describes the behavior of large-scale structures like black holes, and quantum mechanics, which governs the microscopic world of particles? In a sense, black hole lasers represent a convergence of some of the most profound questions in physics. If they exist, they could shed light on some of the deepest mysteries of the universe. The study of black hole lasers could not only help us understand the extreme physics surrounding black holes but could also unlock new insights into the nature of gravity, energy, and quantum mechanics. By continuing to study these theoretical phenomena, scientists are pushing the boundaries of our understanding of the cosmos and moving closer to answering some of the most fundamental questions of all. Looking to the future, the research into black hole lasers could take a variety of different directions. Some scientists may focus on refining the theoretical models to make predictions about how black hole lasers would behave under different conditions, such as in different types of black holes or with varying amounts of surrounding matter. Others may focus on developing new technologies and observational techniques to detect these elusive phenomena. Regardless of the specific approach, one thing is clear: the exploration of black hole lasers represents one of the most exciting frontiers in modern astrophysics. While black hole lasers remain a theoretical phenomenon, they represent an exciting possibility that could significantly alter our understanding of the universe. They challenge our current models of physics and offer new ways of thinking about the relationship between gravity, light, and energy. Though much work remains to be done before we can confirm their existence, the very concept of black hole lasers is a reminder of the vastness of the unknown and the incredible potential for discovery that lies ahead. Whether or not black hole lasers turn out to be real, the pursuit of this knowledge will undoubtedly lead to groundbreaking advancements in science and technology. As we continue our exploration of these theoretical ideas, we are reminded of the importance of curiosity and the quest for knowledge. The search for understanding black holes and the possibility of black hole lasers is not just about solving an academic puzzle. It's about expanding the boundaries of human knowledge and pushing the limits of what we can achieve in our understanding of the universe. And as we venture further into the unknown, we may find that the answers to these questions are even more profound and awe-inspiring than we could have ever imagined. As we delve deeper into the theoretical landscape of black hole lasers, it's important to examine some of the more profound consequences that this phenomenon could have on our understanding of the universe. In essence, black hole lasers aren't just a curiosity of astrophysics. They represent a revolutionary approach to the very fabric of reality. Black holes, with their singularities and event horizons, have long been considered some of the most mysterious and extreme objects in the cosmos. But if black hole lasers were to exist, they would force us to reconsider some of the most fundamental concepts in modern physics, including our understanding of space, time, and energy. The interaction between light and gravity near a black hole already pushes the limits of what we understand about the cosmos. For example, the famous phenomenon of gravitational lensing, where light bends around a massive object like a black hole, is a prime example of how extreme gravity affects the behavior of light. Now, imagine taking that one step further. What if the immense gravitational forces around a black hole could create a mechanism for amplifying energy in the form of coherent electromagnetic radiation, a laser-like beam of light, in a way that we have never seen before? The implications of such a discovery would be profound, not just for astrophysics, but for our understanding of the universe as a whole. When we talk about black hole lasers, we're diving into the heart of some of the most unresolved questions in physics. To understand these questions, we need to explore the current understanding of black holes and their complex interactions with light and matter. At the core of these interactions is the event horizon, the point beyond which nothing can escape a black hole, not even light. This boundary is where the laws of physics as we know them break down, and it's also where the energy dynamics of black hole lasers could potentially take place. One of the biggest mysteries surrounding black holes is the nature of the singularity at their core. A singularity is a point in space where gravitational forces are so intense that space-time curves infinitely, and the laws of physics break down. At the singularity, density and temperature become infinite, and time as we know it ceases to have any meaning. But it's precisely in this extreme environment that the energy amplification we associate with black hole lasers could occur. The question then becomes, can we figure out how to extract energy from a black hole's gravitational field and convert it into a coherent beam of radiation? One avenue of research that holds promise in this regard is the study of accretion disks. An accretion disk forms around a black hole when matter, such as gas or dust, is pulled toward the event horizon. As this matter spirals inwards, it heats up to incredibly high temperatures and emits radiation. Some of this radiation, however, is not just random emissions but may be shaped by the dynamics of the black hole's gravity. In certain models, the matter swirling around the black hole could become so finely tuned that it emits a form of radiation that is coherent and directional, much like the light emitted by a laser. But what sets black hole lasers apart from conventional lasers is the environment in which they would form. Instead of the typical setup for laser creation, such as the interaction of light with specific materials or systems to stimulate the emission of photons, black hole lasers would rely on the extreme gravitational fields near a black hole to amplify and direct energy in a completely novel way. The fundamental mechanics of how this energy is generated, how it is focused, and whether it could exist in a sustained, coherent form are still largely speculative, but they represent a tantalizing possibility for future research. One intriguing theory revolves around the concept of gravitational focusing. This is a phenomenon that occurs when a massive object, like a black hole, bends the path of light passing near it. In a way, it's similar to how a magnifying glass focuses light. Gravitational focusing could potentially be harnessed to concentrate radiation emitted near the event horizon into a narrow, intense beam, essentially creating a laser-like effect. If black holes are capable of focusing light in this way, then black hole lasers might not just be theoretical constructs but could be an actual, detectable phenomenon. Another key factor in understanding black hole lasers is the role of angular momentum. Many black holes, especially those found in the centers of galaxies, are not stationary but rather rotating. The spin of a black hole creates a unique environment in the space surrounding it, known as the ergosphere. This is the region just outside the event horizon where the spacetime itself is dragged by the black hole's rotation, causing all objects within it to move in the direction of the spin. The energy dynamics within the ergosphere are complex and highly energetic, and it is in this region that some theories suggest black hole lasers could form. Theoretical models of black hole lasers also tie into the study of astrophysical jets. These jets are streams of high-energy particles that are often emitted from the poles of supermassive black holes, particularly in active galactic nuclei (AGN). While the exact mechanisms behind the formation of these jets are still not fully understood, it is thought that the magnetic fields generated by the rotating black hole, combined with the accretion disk, play a crucial role. Some researchers hypothesize that the energy from these jets could potentially be harnessed in a way similar to how we envision black hole lasers. If the energy dynamics of these jets could be better understood, it might help scientists refine their models of black hole lasers and provide new insights into the physics of black holes. The study of black hole lasers also invites comparisons to other types of astrophysical phenomena that involve the amplification and emission of energy. One of the most well-known examples is the laser used in a laboratory setting, where specific materials are excited and then emit a highly focused, coherent beam of light. In a black hole, however, the mechanism of amplification is radically different. Rather than using a physical material to stimulate the emission of light, black hole lasers would rely on the gravitational field and the complex interactions between light, matter, and space-time. This distinction makes the theoretical study of black hole lasers both exciting and daunting. If such a phenomenon does exist, it would challenge many of the assumptions we currently have about how energy can be concentrated and emitted in extreme environments. As mentioned earlier, black holes cannot be observed directly, which means that studying them requires highly sensitive instruments that can detect the radiation and gravitational waves they emit. For a phenomenon like a black hole laser to be detected, it would require the development of even more advanced instruments capable of isolating and studying faint signals from distant black holes. Current technologies, such as the Event Horizon Telescope and various space-based observatories, have already made groundbreaking contributions to our understanding of black holes. But the detection of a black hole laser would require an entirely new level of precision, pushing the boundaries of what is currently possible. In the future, we may also see the development of new theories and models that provide more insight into the behavior of black hole lasers. These models would likely draw on both general relativity and quantum mechanics, two areas of physics that are still not fully reconciled with each other. The merging of these two theories is one of the biggest challenges in modern physics, and the study of black hole lasers could provide new opportunities for progress in this area. While the concept of black hole lasers may seem fantastical, it is grounded in some of the most cutting-edge theories in physics today. Whether or not these lasers truly exist in the way that scientists imagine remains to be seen. However, the pursuit of this idea is one of the many ways in which science continually pushes the boundaries of what we know about the universe. It is a testament to humanity's insatiable curiosity and drive to explore the unknown. The search for answers about black hole lasers is far from over, and it is likely to be a central topic in astrophysics for years to come. As we continue to explore the possibility of black hole lasers, it's essential to recognize how this concept connects to some of the most fundamental ideas in modern physics, especially the ongoing challenges faced in unifying quantum mechanics and general relativity. These two pillars of modern physics have long been at odds in many ways, and understanding black hole lasers could provide a unique testing ground for these theories. The tension between quantum mechanics and general relativity arises from their differing descriptions of the universe. General relativity, developed by Albert Einstein, explains the behavior of large-scale structures in the cosmos, like stars, galaxies, and black holes, through the concept of space-time curvature. It beautifully explains phenomena like gravitational waves, the bending of light near massive objects, and the motion of celestial bodies. On the other hand, quantum mechanics governs the behavior of the smallest particles in the universe, things like electrons, photons, and quarks. It operates on principles that seem completely foreign to our everyday understanding of the world, like wave-particle duality, superposition, and entanglement. When applied to black holes, quantum mechanics gives rise to paradoxes like the black hole information paradox, which has puzzled scientists for decades. If black hole lasers do exist, they could provide valuable insight into how these two theories might work together. The behavior of light near the event horizon, the interaction of quantum particles in extreme gravitational fields, and the potential amplification of energy by these cosmic giants could all serve as clues about how gravity operates on quantum scales. In other words, black hole lasers may offer a glimpse into a unified theory of quantum gravity, which remains one of the most sought-after goals in theoretical physics. One possible connection between black hole lasers and quantum mechanics is the idea of Hawking radiation. Proposed by Stephen Hawking in 1974, Hawking radiation is a theoretical process in which black holes emit radiation due to quantum effects near the event horizon. According to this theory, pairs of virtual particles are constantly being created and annihilated in empty space. Near the event horizon of a black hole, these particles can be separated by the immense gravitational forces, with one particle falling into the black hole and the other escaping as radiation. This radiation could, in theory, be detected as part of a broader understanding of the black hole's energy dynamics. In the context of black hole lasers, it's possible that Hawking radiation could play a role in the amplification of energy near a black hole. If virtual particles were indeed separated in a way that allowed for energy to escape the black hole's gravitational grip, it could potentially form a coherent beam of radiation, much like a laser. However, this idea is still speculative, and has not been proven in practice. Hawking radiation itself is incredibly weak and difficult to detect, making it a challenging phenomenon to study. Moreover, understanding black hole lasers could lead to new insights into the properties of spacetime itself. The extreme conditions near a black hole's event horizon may reveal how spacetime behaves at its most fundamental level. For instance, the nature of spacetime near a black hole could offer insights into the fabric of the universe itself, including its possible structure at the quantum level. This is where theories such as string theory, which suggests that the fundamental particles of nature are actually one-dimensional strings, come into play. String theory offers a possible framework for reconciling general relativity with quantum mechanics, and black hole lasers may provide a new way to test these ideas. One of the other major theoretical frameworks that could intersect with black hole lasers is the idea of exotic matter. Exotic matter is a theoretical form of matter that possesses properties opposite to that of normal matter. In particular, it is hypothesized that exotic matter could have negative mass, which would allow it to counteract the effects of gravity. While exotic matter is still purely speculative, and has not been observed, its potential role in black hole lasers is an exciting avenue for future exploration. In some models, it's suggested that the intense gravitational fields near a rotating black hole could, in theory, interact with exotic matter in such a way that it would amplify electromagnetic radiation into a coherent beam. This exotic matter might be created or captured by the black hole's accretion disk, which could then act as a sort of stimulant for the emission of coherent radiation. While this is highly speculative, it shows how black hole lasers could draw from a wide range of theoretical ideas to explain their possible existence. Another fascinating area of exploration lies in the connection between black hole lasers and quantum entanglement. Quantum entanglement occurs when two particles become correlated in such a way that the state of one particle instantly affects the state of the other, even if they are separated by vast distances. This phenomenon has been experimentally observed, but it remains one of the most mysterious aspects of quantum mechanics. Entanglement is often described as spooky action at a distance, because it seems to defy our classical understanding of how information and energy can be transmitted. In the context of black hole lasers, it's possible that quantum entanglement could play a role in the way energy is amplified and emitted. For example, the radiation emitted by a black hole's accretion disk could become entangled with the gravitational field, creating a system in which information about the energy dynamics of the black hole is shared across vast distances. This could potentially explain how energy is focused into a narrow, coherent beam, a crucial characteristic of a laser. Moreover, if black hole lasers are indeed possible, they could have profound implications for our understanding of energy production and the limits of physics. Harnessing energy from black holes would represent a monumental leap forward in energy science, pushing the boundaries of what we thought was possible. It could open up entirely new avenues for space exploration, as the energy produced by black holes could be harnessed for future spacecraft propulsion systems. Imagine, for a moment, a spacecraft equipped with technology capable of extracting energy from a black hole laser, enabling it to travel across the vast distances of space at speeds previously thought impossible. As we continue to probe the depths of this theoretical phenomenon, the practical challenges remain immense. One of the primary obstacles is the sheer distance of black holes from Earth. Most black holes are located far beyond our solar system, making direct observation and measurement incredibly difficult. Even the closest black hole to Earth, the 616 Monocerotis, is located about 3,000 light-years away. This means that detecting a black hole laser, if one were to exist, would require an unprecedented level of sensitivity and precision in our observational instruments. Currently, astrophysicists rely on a variety of tools to study black holes, including radio telescopes, space-based observatories, and gravitational wave detectors. These instruments have already provided us with valuable insights into the behavior of black holes, such as the recent detection of gravitational waves from black hole mergers. However, detecting a black hole laser would require a new kind of observational technology, one capable of isolating faint signals of energy in the form of coherent radiation. This could involve the development of specialized detectors that can measure the minute variations in electromagnetic fields caused by the presence of a black hole's energy emissions. Moreover, detecting black hole lasers would require not just new technology but also new theoretical models to guide our observations. Scientists would need to develop more accurate simulations of black hole behavior in order to predict how energy is amplified and emitted in the form of laser-like beams. These models would need to account for the complexities of space-time curvature, the interaction between light and gravity, and the behavior of matter under extreme conditions. Black hole lasers represent one of the most intriguing and speculative phenomena in modern astrophysics. While the concept is still largely theoretical, it offers a unique window into the most extreme environments of the universe. The discovery of black hole lasers, if they exist, could transform our understanding of energy, gravity, and the very fabric of spacetime itself. It would challenge existing theories and open up new frontiers of exploration in the realm of quantum mechanics, general relativity, and cosmology. For now, the pursuit of black hole lasers remains one of the many mysteries waiting to be unraveled in the depths of space. As we delve further into the theoretical implications of black hole lasers, we begin to see how this concept could challenge not just our understanding of the cosmos but also our very understanding of the physical laws that govern the universe. The study of black holes, in general, has already led to revolutionary insights, such as the confirmation of gravitational waves and the imaging of a black hole's event horizon. But black hole lasers, if they exist, could offer an even more profound shift in the way we think about energy and spacetime. One of the most fundamental questions that would be raised by the discovery of black hole lasers is, how would energy behave in such extreme conditions? It is well known that black holes are regions of spacetime where gravity is so intense that not even light can escape. This fact alone makes it seem counterintuitive that a black hole could emit coherent radiation like a laser. However, if we consider the theory that the accretion disk of a black hole could serve as the source of energy amplification, it begins to make more sense. The interaction of matter, light, and gravitational forces near a black hole might create the right conditions for the formation of a laser-like beam. One of the most interesting aspects of this idea is the role that angular momentum might play in the process. Black holes that spin rapidly, known as Kerr black holes, are thought to possess a unique property that could facilitate the creation of black hole lasers. These spinning black holes create what is known as an ergosphere, a region outside the event horizon where spacetime itself is dragged along by the black hole's rotation. This effect is called frame dragging, and it could potentially interact with the surrounding accretion disk in a way that amplifies radiation and causes it to emerge in a narrow, coherent beam. The concept of frame dragging could be key to understanding how a black hole might act as a laser. In this scenario, the intense rotation of the black hole could cause particles in the accretion disk to move at incredibly high speeds, generating electromagnetic radiation. This radiation could be amplified by the extreme gravitational field near the black hole, producing a laser-like effect. The idea of a rotating black hole interacting with its environment in this way is already part of our understanding of black hole dynamics, but the possibility that it could lead to the creation of a coherent, amplified beam of light is still very much a topic of ongoing research and debate. In a similar vein, the phenomenon of gravitational lensing could also play a role in the formation of black hole lasers. Gravitational lensing occurs when a massive object, like a black hole, bends the path of light passing nearby due to its intense gravitational field. This effect has been observed in many parts of the universe, often revealing distant galaxies and other cosmic objects that would otherwise be hidden from view. It's conceivable that the intense gravitational field near a black hole could focus light in a way that produces a beam of radiation. If this beam were coherent, it could resemble the properties of a laser, with the radiation being amplified and focused into a narrow, highly concentrated beam. As we consider the theoretical models for black hole lasers, it's important to acknowledge that the precise mechanics of this phenomenon are still largely unknown. One major challenge in understanding black hole lasers is the lack of observational evidence. While scientists have been able to detect many aspects of black holes, such as the gravitational waves produced by their collisions and the radiation emitted by their accretion disks, no one has yet observed a coherent beam of light emanating from a black hole in the way that we would expect from a laser. One of the primary reasons for this is the immense distance between Earth and the black holes we study. The closest known black hole to Earth, V616 Monocerotis, is still over 3,000 light-years away. This makes it incredibly difficult to detect any faint signals or radiation emanating from the vicinity of a black hole. Even with advanced telescopes and observatories, capturing a clear and detailed image of a black hole laser would require technology far beyond what we currently have at our disposal. Another challenge lies in the fact that black holes are typically surrounded by a chaotic and dynamic environment. The accretion disk, for example, is not a uniform structure. It is constantly changing and evolving, with material spiraling into the black hole at varying speeds and angles. This turbulence makes it difficult to predict how radiation would behave near a black hole, let alone whether it could be amplified into a laser-like beam. Despite these challenges, the idea of black hole lasers remains an exciting area of theoretical research. If such a phenomenon were ever detected, it would not only revolutionize our understanding of black holes but also lead to new breakthroughs in fields like energy production and space exploration. The ability to harness energy from a black hole, for instance, could provide a nearly limitless source of power. This could have profound implications for future space missions, enabling spacecraft to travel farther and faster than ever before. Moreover, the study of black hole lasers could help us answer some of the most fundamental questions in physics. For example, it could shed light on the behavior of matter and energy under extreme conditions, helping to reconcile the discrepancies between quantum mechanics and general relativity. This could ultimately lead to a unified theory of quantum gravity, which has long been one of the most elusive goals in physics. The existence of black hole lasers would also have profound implications for our understanding of the universe as a whole. It could provide evidence for the existence of exotic matter or new forms of energy that we have yet to fully comprehend. Additionally, the discovery of a black hole laser could lead to the development of new technologies that could revolutionize the way we generate and use energy. Whether in the realm of space travel, communication, or even more practical applications on Earth, the potential benefits of black hole lasers are vast and far-reaching. While we have yet to confirm the existence of black hole lasers, the theoretical work being done today will continue to pave the way for future discoveries. As our understanding of black holes and the extreme conditions near them grows, so too will our ability to explore and harness the power of these cosmic giants. Black hole lasers may very well be one of the next great frontiers of scientific exploration, offering us new insights into the nature of the universe and the forces that shape it. For now, the idea of black hole lasers remains speculative, but the questions they raise are fundamental to our understanding of the cosmos. Whether or not we will ever detect such a phenomenon is still uncertain, but the pursuit of answers will undoubtedly lead to more groundbreaking discoveries in the future. The search for black hole lasers, like the search for other hidden phenomena in the universe, is a journey that will continue to push the boundaries of science and human knowledge. Now imagine placing a reflective barrier around a spinning black hole, not physically, of course, but theoretically, perhaps a natural structure or quantum boundary in space. What happens then is similar to building a laser cavity. In a laser, photons bounce between mirrors, gaining strength as they pass through an amplifying medium. In the case of a black hole laser, certain modes of light or scalar waves trapped between the black hole and this hypothetical reflective boundary could undergo repeated amplification through the process of superradiance. Each time the wave bounces off the boundary and interacts with the black hole's ergosphere, it extracts more energy, growing exponentially in amplitude until it escapes in the form of a coherent, high-energy beam. This is the heart of the black hole laser concept, a natural astrophysical system mimicking the mechanism of an artificial laser, using gravitational energy instead of electrical input, space-time curvature instead of mirrors, and quantum fields instead of a gain medium. While this may sound purely hypothetical, it's grounded in serious theoretical work. The idea was first explored in depth by physicists such as William Unruh, who extended these concepts by creating analogs in laboratory settings to simulate black hole conditions using fluids and light. Unruh's analog black holes, systems where sound waves behave similarly to how light would behave near a black hole, opened up a new realm of investigation. By studying how these sound waves, or phonons, become trapped, amplified, and possibly turned into coherent emissions, researchers hope to gain insight into how real black hole lasers might behave. These analog systems also provided a testing ground for Hawking radiation, another key element that intersects with black hole laser theory. Hawking radiation itself arises from quantum field theory in curved spacetime. It suggests that black holes aren't entirely black. They emit tiny amounts of radiation due to quantum fluctuations at the event horizon. In the black hole laser model, these quantum fluctuations can be seen as the seed, the initial disturbance that, when caught in the right conditions, becomes amplified through superradiance. This ties into one of the most important implications of black hole lasers, their role in potentially resolving the black hole information paradox. The black hole information paradox questions what happens to information that falls into a black hole. Quantum theory says information can't be destroyed, but general relativity suggests it vanishes forever once it crosses the event horizon. Hawking radiation, in its simplest form, seems to carry no information, which deepens the mystery. However, if black holes can emit radiation in a coherent, structured form, like a laser beam, it raises the possibility that information isn't lost after all. Instead, it could be encoded in the pattern of the emitted radiation, structured through the same amplifying mechanism that makes lasers coherent. This idea is still speculative, but it has captivated the minds of physicists exploring the interface of quantum mechanics, gravity, and thermodynamics. It suggests that the universe might be far more connected and dynamic than we currently realize. Black holes, long thought to be simple engines of destruction, could instead be engines of information processing, capable of emitting meaningful patterns of radiation shaped by the intense interactions of space-time, energy, and quantum particles. And it gets even more fascinating when we consider the role of scalar fields in this context. Scalar fields are simpler than vector fields like the electromagnetic field, and some physicists propose that certain particles, perhaps even hypothetical particles like axions, could create the perfect conditions for superradiant amplification around a rotating black hole. If these scalar waves form a cloud around the black hole, they can feed off its rotational energy through superradiance, growing in strength and possibly leading to periodic bursts of radiation, another variation of a black hole laser, but one modulated by the presence of exotic fields. Some theories even go as far as to suggest that these scalar clouds could produce gravitational waves, allowing us to detect black hole laser activity indirectly. If true, it would mean our gravitational wave observatories like LIGO or Virgo could one day pick up signatures not just of collisions or mergers, but of energy extraction events powered by black hole lasers, a profound leap in our observational capabilities. But these aren't just theoretical fantasies. Computer simulations have already started to model what such phenomena might look like. These simulations explore how different wave modes behave near spinning black holes, how boundaries can trap and reflect waves, and how the entire system might evolve over time. What they suggest is that under the right conditions, black hole lasers could indeed exist, at least as a natural amplification process. The consequences would ripple across multiple domains of science. If we could observe even indirect evidence of a black hole laser, it would challenge our understanding of entropy, thermodynamics, and the limits of energy extraction in the universe. It would force us to ask new questions. Can we harness this energy? Could advanced civilizations use black hole lasers as cosmic beacons or power sources? Could they be responsible for some of the unexplained high-energy signals we receive from deep space? These questions are more than science fiction. They represent the natural progression of inquiry when our imagination and mathematics extend into the extreme corners of the cosmos. We know black holes are capable of bending light, twisting time, and swallowing stars. But what if they could also shine, not with chaotic, random energy, but with the precision and coherence of a cosmic laser? Hawking radiation, proposed by Stephen Hawking in 1974, is one of the most astonishing consequences of merging quantum theory with general relativity. According to this concept, black holes are not entirely black. They emit tiny amounts of thermal radiation due to quantum effects near the event horizon. This radiation arises from particle-antiparticle pairs that spontaneously appear near the horizon. If one particle falls into the black hole while the other escapes, it appears as though the black hole is emitting energy. Over extremely long timescales, this could even cause the black hole to evaporate entirely. Now, when we link Hawking radiation to the concept of black hole lasers, we find an intriguing synergy. Hawking radiation involves the creation of particles near the event horizon, and these particles can interact with the geometry and quantum fields surrounding the black hole. In a black hole laser scenario, it's possible that the same quantum fluctuations that lead to Hawking radiation could be involved in the seeding of the waves that are then amplified through superradiance. If certain modes of these fluctuations are reflected back towards the black hole, again, by some natural or effective boundary, they could create a feedback loop. This feedback mechanism could sustain the emission of coherent radiation, analogous to how laser light is produced. Theoretical work has explored these ideas further, especially in lower-dimensional space-time models, where the mathematics is simpler but still insightful. In such models, black hole analogs can be built using condensed matter systems or Bose-Einstein condensates, ultra-cold gases where quantum effects can be observed on macroscopic scales. These setups have shown that under the right conditions, spontaneous amplification of quantum fluctuations can occur, and coherent emissions, true analog lasers, can emerge from simulated event horizons. If these laboratory analogs can replicate the behavior predicted in astrophysical settings, then black hole lasers may not be just a thought experiment, but a profound physical reality waiting to be confirmed. Moreover, the implications extend far beyond theoretical interest. If black hole lasers do exist, they could explain certain astrophysical observations that currently lack a clear cause. For instance, some gamma-ray bursts, intense flashes of high-energy radiation observed in distant galaxies, have properties that are not entirely explained by existing models of stellar collapse or neutron-star mergers. Could some of these events be the result of black hole laser emissions? While there is no direct evidence yet, the idea remains tantalizing. Another area where black hole lasers could have an impact is in the study of dark matter. Some theoretical models propose that certain kinds of dark matter, such as ultralight bosons, could become trapped around rotating black holes and form clouds that interact with superradiant processes. These clouds could serve as the reflective boundary needed for a black hole laser to form. Over time, the trapped bosons could amplify and emit energy in narrow beams, potentially detectable through gravitational wave observations or gamma-ray telescopes. If confirmed, this would be not only a major breakthrough in black hole physics, but also a groundbreaking discovery in the ongoing quest to understand dark matter. In addition, black hole lasers might offer insight into the long-standing black hole information paradox. If coherent radiation can be emitted by a black hole through these mechanisms, then perhaps some form of information is preserved or encoded in the emitted light. Unlike Hawking radiation, which is thermal and seemingly random, laser-like emissions would be highly ordered and might carry imprints of the matter that fell into the black hole. This could open a new line of inquiry into how information escapes black holes and how the laws of physics preserve the integrity of quantum data, a problem that has perplexed scientists for decades. We also cannot ignore the role of quantum field theory in curved spacetime, a framework used to analyze particle behavior near black holes. In this framework, the vacuum is not empty but teems with virtual particles, and the curvature of spacetime affects how these particles behave. This is essential to understanding both Hawking radiation and black hole lasers. The geometry around a rotating black hole creates conditions where these fields can support wave amplification, and the presence of boundaries, real or effective, can lead to standing wave patterns, a hallmark of laser-like systems. Even string theory and loop quantum gravity, two leading contenders for a theory of quantum gravity, have speculated about the exotic physics that might emerge near black holes. In these frameworks, the fabric of spacetime itself is quantized, and extreme environments like black holes could be windows into those quantum structures. If black hole lasers exist, they might not only be a phenomenon of classical general relativity and quantum field theory but also a manifestation of deeper, more fundamental laws of nature. The black hole laser remains one of the most fascinating theoretical constructs in modern astrophysics. It weaves together superradiance, quantum mechanics, general relativity, and even elements of cosmology and particle physics. While no direct observations have yet confirmed their existence, the theoretical groundwork is rich and growing. As our tools for observing the universe improve, from gravitational wave detectors to high-energy particle telescopes, we may soon uncover the first hints of these extraordinary cosmic light machines. They may not just change how we see the universe, they could change what we know about the deepest workings of reality. This idea leads us to a fascinating consequence. If black hole lasers are real, they could be observable. Astrophysicists have long speculated about the sources of extremely high-energy emissions in the universe: gamma-ray bursts, ultra-high-energy cosmic rays, and certain quasars that shine brighter than entire galaxies. While many of these phenomena have been attributed to conventional astrophysical processes like supernovae or matter accreting onto black holes, it's possible that a subset of these intense emissions could be due to black hole laser activity. Imagine a rotating black hole surrounded by a dense cloud of exotic particles or scalar fields. These fields could form a kind of mirror, not in the reflective sense we're familiar with, but in the sense that they can trap and scatter certain modes of radiation. When these waves interact with the black hole's ergosphere, they get amplified and bounce back, again and again, growing stronger each time. Eventually, they could explode outward as a powerful, focused beam of energy, an astrophysical laser not powered by electricity or chemistry, but by the rotational kinetic energy of a collapsed star. In some theories, the reflective barrier could be provided by a phenomenon known as a massive bosonic field. These fields, proposed in various extensions of the standard model of particle physics, consist of particles that have mass and can form cloud-like structures around black holes. When these fields interact with a rotating black hole, superradiant instabilities can occur, leading to the exponential growth of particular wave modes trapped in orbit around the black hole. This creates the exact conditions needed for a black hole laser, a feedback loop of radiation growing stronger with each pass. The possibility that this process could be occurring across the universe, undetected, misunderstood, or hidden within broader astrophysical phenomena, is exhilarating. It means that some of the brightest, most mysterious cosmic events might not just be the result of matter collapsing or exploding, but could be a glimpse into the deep interplay of quantum fields and space-time curvature. And it also means that black hole lasers, while exotic and rare, could leave observable imprints in the form of specific energy spectra, polarization patterns, or timing structures in the light they emit. The possibility that this process could be happening naturally in the cosmos is as thrilling as it is mysterious. If black hole lasers do exist, they could provide explanations for some of the most puzzling energetic events we've ever observed. The sheer power output from such a mechanism would rival, or even surpass that of traditional astrophysical explosions, but with a signature that could look very different, more collimated, more coherent, and potentially even modulated in ways that might one day allow us to identify them distinctly from other cosmic sources. But beyond astrophysical implications, black hole lasers also raise profound questions about the nature of spacetime, quantum fields, and information. One of the enduring mysteries in physics is the black hole information paradox. Whether information that falls into a black hole is truly lost forever, violating quantum mechanics, or if it somehow escapes, possibly through phenomena like Hawking radiation. If black hole lasers are real and involve the amplification and emission of quantum fluctuations, could they be involved in the leakage of information from black holes? Could the coherent radiation they emit carry imprints of the quantum fields and particles that once fell into the event horizon? This bridges black hole laser theory with quantum information theory, and potentially with quantum gravity, the elusive theory that aims to reconcile general relativity and quantum mechanics. In this view, the coherent radiation from a black hole laser might be more than just energy. It might be a language, a structured, information-rich emission encoded with the history of the black hole's interactions with its surroundings. This idea nudges us closer to a concept known as soft hair, introduced in theoretical frameworks trying to resolve the information paradox. According to this theory, black holes might possess subtle quantum properties, hairs, so to speak, that record information and could influence outgoing radiation. If the structure of these hairs affects the dynamics of superradiance, or quantum fluctuations near the event horizon, then black hole lasers might act as amplifiers of these microscopic fingerprints. And this opens a truly staggering possibility. The cosmos could be scattered with natural lasers transmitting quantum information across the vastness of space. These beams, encoded with the complex patterns of the fields that birth them, may be the universe's most powerful and precise storytellers, broadcasting the hidden dynamics of black holes to anyone capable of decoding the message. Not metaphorically, but literally, if only we can learn to understand the language. Now let's shift our lens slightly and look deeper into how analog gravity experiments have helped solidify the plausibility of black hole lasers. In laboratory settings, physicists have created what are known as acoustic black holes, regions where sound waves can become trapped, just as light is trapped by gravitational black holes. These experiments often involve flowing fluids or Bose-Einstein condensates where the flow velocity exceeds the speed of sound, creating a kind of acoustic event horizon. In these setups, researchers have observed phenomena strikingly similar to Hawking radiation and superradiant scattering. But more interestingly, in certain configurations, they've seen the onset of instability, feedback loops where wave modes grow in intensity. These lab-based observations give credence to the idea that nature, under the right conditions, can create systems with the essential ingredients of black hole lasers. What's particularly important about these analog experiments is that they allow scientists to control and tune the parameters in ways that are impossible in real black holes. They can adjust the rotation, the shape of the potential barrier, the properties of the quantum fields, and directly observe the onset of amplification. Through these carefully crafted conditions, they've demonstrated that even small instabilities can lead to exponential growth, mirroring the theoretical predictions of black hole lasers and validating them in a tangible, experimental form. And here's where things begin to loop together. If the same quantum instabilities that cause Hawking radiation and superradiance can create a coherent, laser-like output in an analog system, then the idea that astrophysical black holes could do the same isn't just science fiction, it's testable physics, grounded in experiment. The beauty of these analog gravity experiments lies in their ability to recreate essential features of black holes in a controlled setting. Although we can't yet observe black hole lasers directly from a distant black hole in a faraway galaxy, these experiments act as laboratories for phenomena that might otherwise take centuries or longer to be confirmed. The principle behind this is simple. We simulate the core behaviors of black holes using accessible materials and systems that behave similarly, allowing us to test theories and make predictions that might one day apply to the cosmos itself. At the heart of the black hole laser idea is the fundamental concept of superradiance, which occurs when certain waves, whether they're light, sound, or even quantum fluctuations, are amplified as they interact with a rotating black hole. When these waves interact with the event horizon, they extract energy from the black hole's rotation, a process that leads to the exponential growth of the wave's intensity. If the conditions are right, this amplification can result in an output of coherent radiation, much like a laser beam. This brings us to an interesting question. Could black hole lasers be observed in real time in the distant universe? While we can't yet detect them directly, the potential for their discovery depends on the type of black hole involved, its size, and the environment around it. The most likely candidates are rapidly spinning supermassive black holes, which reside at the centers of galaxies. These black holes possess immense gravitational forces and are often surrounded by dense accretion disks made of hot, ionized gas. The interaction between these powerful gravitational fields and the surrounding matter could, in theory, create the perfect conditions for black hole lasers. For instance, in the case of quasars, some of the brightest and most energetic objects in the universe, supermassive black holes are actively pulling in massive amounts of gas. As this gas spirals toward the black hole, it heats up to extreme temperatures, emitting high-energy radiation in the form of X-rays and gamma rays. These quasars could be prime candidates for black hole laser activity, where the energy generated by the black hole's rotation and the accretion disk could lead to coherent beams of radiation being emitted from the region around the event horizon. Furthermore, it's not just about the black hole itself, but also about the surrounding environment. Black holes surrounded by certain types of exotic fields, like scalar fields or bosonic clouds, may amplify specific types of radiation in a way that generates a laser-like output. These fields, which have been theorized in various models beyond the standard model of particle physics, could provide the mirror needed to trap and amplify waves near the event horizon. The interaction between the rotating black hole and these fields could result in the emission of coherent, collimated beams of energy, similar to what we observe with lasers on Earth. To detect these black hole lasers, astronomers would likely need to look for specific signatures in the radiation coming from the black hole's vicinity. These signatures could include unique patterns of light polarization, specific energy spectra, or temporal fluctuations that are consistent with the theoretical models of black hole lasers. In essence, the emitted radiation might behave in a way that is unlike anything we've observed from other cosmic sources. With the right detection equipment, astronomers could look for these subtle cues and begin to identify potential black hole lasers in the universe. The idea that black hole lasers could exist has profound implications for our understanding of the cosmos. First, it would offer a new way to probe the interior dynamics of black holes. Since we cannot directly observe the inside of a black hole due to the event horizon, the radiation emitted from a black hole laser could act as a kind of window into its inner workings. By studying these emissions, scientists could gain insights into the extreme physics of black holes, such as the nature of spacetime near the event horizon, the properties of the quantum fields involved, and the effects of rotation on the black hole's energy and matter. Moreover, black hole lasers could also offer new perspectives on the role of black holes in the larger structure of the universe. These lasers might play a crucial role in the energy balance of galaxies, potentially influencing star formation and the distribution of matter. In this way, black hole lasers could be a missing link in our understanding of galactic dynamics and the evolution of the universe as a whole. On a more speculative level, the discovery of black hole lasers might even have technological implications for humanity's understanding and manipulation of energy. If we can understand how black holes produce such extreme emissions, we might one day learn to harness the principles behind them for our own use. Imagine the ability to create energy sources on the scale of a black hole's power output, or to understand how to manipulate space-time itself for use in future propulsion systems. These ideas are still firmly in the realm of science fiction, but the potential for revolutionary breakthroughs in physics and technology is undeniable. As we continue to explore these theoretical concepts, it's important to remember that black hole lasers, while compelling, remain speculative. Much more research is needed to confirm whether this phenomenon truly exists in the cosmos. We must also keep in mind the challenges of observing such distant and enigmatic objects. Despite the advances in observational astronomy, the study of black holes is still in its early stages, and many of the most fundamental questions about their nature remain unanswered. The study of black hole lasers represents one of the cutting edges of modern theoretical physics. By investigating how quantum fields interact with black holes and how superradiance might lead to coherent radiation, we are pushing the boundaries of what we know about the universe. Whether or not black hole lasers are eventually discovered, the pursuit of this idea will undoubtedly yield new insights into the nature of black holes, the fabric of spacetime, and the fundamental forces that govern the cosmos. As our technology advances and our theoretical models become more sophisticated, we may one day be able to observe black hole lasers directly, unlocking a new chapter in our understanding of the universe. For now, we can only speculate about the possibility, marvel at the elegance of the theory, and imagine the profound implications it could have for the future of science and technology. The pursuit of understanding black hole lasers is as much about discovering new realms of astrophysics as it is about testing the very limits of our knowledge. We stand at the threshold of an era where the intersection of quantum mechanics, general relativity, and high-energy astrophysics might reveal not just the mechanisms of black holes, but new phenomena that have never before been envisioned. The possibility of black hole lasers introduces questions that challenge our fundamental understanding of physics. Could it be that black holes, long thought to be inscrutable and nearly completely isolated systems, are actually some of the universe's most powerful and complex emitters of radiation, capable of creating natural lasers? The nature of the universe itself is often paradoxical. While black holes are famously known for their immense gravitational pull, which even light cannot escape, the theory of black hole lasers suggests that there could be situations where black holes not only release energy but do so in a highly structured, coherent form. This apparent contradiction, how an object that traps everything might also release a focused, coherent beam of energy, is a prime example of the mysteries that still define much of modern astrophysics. It speaks to the complexity of these celestial giants and how little we truly understand about their role in the cosmos. Looking deeper into the theoretical framework of black hole lasers, it's crucial to explore the kind of fields and quantum fluctuations that could give rise to such phenomena. In this context, scalar fields, those that don't have a direction or orientation in space but still carry energy, emerge as one of the most promising candidates for driving black hole laser activity. These fields, if sufficiently dense and properly aligned with a rotating black hole, could interact with the black hole's rotational energy, creating conditions ripe for amplification. In turn, these fields could contribute to the emergence of superradiant scattering, where waves grow stronger as they interact with the event horizon. A key point in understanding black hole lasers is the role of angular momentum. In the case of rapidly rotating black holes, such as Kerr black holes, the spin rate dramatically affects the surrounding spacetime. These black holes are not merely points of infinite density. They possess angular momentum that bends spacetime in profound ways. The idea that such a rotating black hole could be a source of coherent radiation hinges on the interaction between its spin, the quantum fields in its vicinity, and the electromagnetic fields generated by the surrounding accretion disk. If conditions are right, the amplified radiation from the superradiant effect could form into a coherent beam, much like the laser beams we create here on Earth. It is in this zone, close to the event horizon, that the fabric of space and time becomes increasingly malleable, warping and distorting under the influence of the black hole's immense gravitational field. Here, quantum effects become more pronounced, and traditional physics begins to break down. The interplay between these quantum effects and classical gravitational theory could allow for a quantum-based laser-like emission. This would mean that the black hole laser phenomenon isn't just a dramatic, high-energy event but a fundamental demonstration of how quantum mechanics and general relativity could be reconciled under extreme conditions. For astrophysicists, the implications of such a discovery would go far beyond simply identifying a new type of astronomical phenomenon. It would be a breakthrough in understanding how the universe operates at its most extreme scales. We would learn more about how black holes interact with the quantum fields that permeate space itself, and this knowledge could have profound consequences for our understanding of spacetime, quantum gravity, and even the fundamental nature of reality. While we still have a long way to go before we can confirm the existence of black hole lasers, the theoretical underpinnings are robust enough to justify further exploration. With advancements in observational technology, such as the Event Horizon Telescope, which recently captured the first image of a black hole's event horizon, scientists are now more capable than ever of studying the most distant and extreme regions of the cosmos. As we continue to push the boundaries of what we can observe, we may one day detect the kind of radiation or laser-like emissions that black hole laser theory predicts. One of the key challenges in proving the existence of black hole lasers is distinguishing their radiation from other high-energy emissions we observe in the universe. Black holes are already known to be potent sources of X-rays, gamma rays, and other forms of electromagnetic radiation. However, the highly focused, coherent nature of laser emissions would offer a different signature, one that might be detectable through advanced telescopes and other instruments sensitive to specific wavelengths of light. Moreover, the subtle quantum signatures predicted by black hole laser theory could provide additional clues to their existence. By carefully analyzing the spectra and polarization of radiation emitted by known black holes, we might one day uncover the faintest traces of these laser-like phenomena. Even in the absence of direct evidence, the theoretical exploration of black hole lasers offers valuable insights into how we might study the universe in the future. The concept of black hole lasers could inspire new research into quantum field theory, gravitational wave astronomy, and the behavior of light in extreme gravitational fields. Each new theory, each new model, helps us piece together the puzzle of how black holes influence the fabric of spacetime, matter, and energy. Moreover, the potential discovery of black hole lasers could prompt new approaches to understanding how information behaves in the presence of extreme gravitational forces. One of the greatest unsolved problems in theoretical physics is the so-called black hole information paradox. When matter falls into a black hole, it is widely believed that the information about that matter is lost to the universe, violating the principles of quantum mechanics. However, if black holes emit coherent radiation in the form of a laser, could it be that some form of information is encoded in that radiation? Could black hole lasers provide the key to resolving this paradox? If so, the discovery would not just be a triumph in astrophysics, but also in the deeper quest for understanding quantum mechanics and the nature of reality itself. The study of black hole lasers could also have profound implications for the future of technology. While the distances involved in black hole observations are far beyond anything practical for human use, the principles that govern the emission of energy from black holes could one day inform the development of new technologies. For example, understanding how black holes amplify and focus energy could lead to innovations in power generation, propulsion systems, and even communications. These applications may seem far-fetched today, but as we continue to explore the universe's extreme environments, the technologies we develop often have unintended, yet far-reaching, consequences. As we look ahead, the search for black hole lasers will undoubtedly inspire new theories, experiments, and discoveries that will shape our understanding of the universe. Whether or not we eventually confirm the existence of these extraordinary cosmic phenomena, the pursuit of knowledge about black holes, superradiance, and quantum fields will continue to push the frontiers of science. The quest to unlock the secrets of black hole lasers is a reminder of the vastness of the unknown and the ever-present drive to explore, understand, and ultimately control the forces of nature that govern our universe. The search for black hole lasers not only takes us deeper into the nature of black holes but also into the core of how we understand the interactions between matter and energy at the most fundamental levels. As we begin to understand more about the quantum and relativistic effects that come into play near the event horizon, we find ourselves confronting some of the deepest mysteries in physics. Black hole lasers, in this sense, are more than just an astronomical curiosity. They represent a potential bridge between the classical physics of general relativity and the quantum world of subatomic particles. One of the most fascinating aspects of black hole laser theory is the role of quantum fields near the event horizon. According to quantum theory, even the vacuum of space is not truly empty. Instead, it is filled with virtual particles that constantly pop in and out of existence. These fluctuations in the quantum field can have significant effects on nearby objects, including black holes. It's within this quantum sea that we begin to glimpse how black hole lasers might emerge. As quantum fields interact with the black hole's intense gravitational field, they can create conditions that amplify certain types of radiation. If this process can be harnessed, it might lead to the creation of highly energetic, coherent light, something akin to a cosmic laser. This interplay between quantum fluctuations and gravity lies at the heart of many current theoretical studies. If black holes are indeed capable of producing coherent laser-like emissions, understanding the underlying mechanisms would require a deeper exploration of the quantum properties of black holes. In particular, researchers are investigating how the quantum fields inside black holes might interact with the event horizon and the singularity at the center. This could provide crucial insights into the nature of space-time itself and the limits of our understanding of quantum gravity. One important consideration in black hole laser theory is the concept of Hawking radiation, a theoretical prediction made by physicist Stephen Hawking in the 1970s. According to Hawking's theory, black holes are not completely black. Instead, they emit a faint radiation due to quantum effects near the event horizon. This radiation is known as Hawking radiation, and it has profound implications for our understanding of black holes. If black holes can emit radiation, could they also be capable of producing coherent, amplified emissions in a form similar to a laser? This question is a key piece of the puzzle when it comes to black hole lasers. Another factor that plays a role in the black hole laser theory is the phenomenon known as superradiance. Superradiance occurs when waves interact with a rotating black hole in such a way that the waves gain energy, becoming more intense as they approach the event horizon. This process, which has been observed in various theoretical models, could provide the necessary amplification for the creation of a black hole laser. When a field or wave interacts with a rapidly rotating black hole, it can lose energy, but under the right conditions, it could also gain energy, leading to the amplification of the wave. This amplification could theoretically lead to the formation of a focused, coherent beam of energy, a laser. To test the theory of black hole lasers, scientists will need to observe the signatures of superradiance and other quantum effects in the radiation emitted by black holes. This is where the growing capabilities of telescopes and other observational tools come into play. Instruments like the Event Horizon Telescope, which recently captured the first-ever image of a black hole's event horizon, are pushing the boundaries of what we can observe in the universe. With these advanced technologies, astronomers may one day be able to detect the subtle differences between the chaotic radiation typically emitted by black holes and the highly structured, coherent emissions that might come from a black hole laser. While direct observation of black hole lasers is still far beyond our current technological reach, scientists are working on various theoretical models to predict the kinds of radiation that would be produced by such phenomena. These models take into account a wide range of factors, including the mass, spin rate, and charge of the black hole, as well as the nature of the surrounding quantum fields. By simulating the conditions near the event horizon of a black hole, researchers can test their hypotheses about how these fields might behave and whether they could give rise to laser-like emissions. One of the challenges in proving the existence of black hole lasers is the immense distances between us and the black holes that might host them. The nearest known black hole, for instance, is located about 1,000 light-years away from Earth. Even with advanced telescopes, detecting such faint, distant phenomena requires careful analysis of the light and radiation emitted by the black hole. The type of radiation we would expect from a black hole laser would likely be very specific, and distinguishing it from other types of radiation would require incredibly precise instruments. It's also important to consider the potential consequences of discovering black hole lasers. Beyond the immediate impact on astrophysics, such a discovery could reshape our understanding of the fundamental forces of the universe. If black hole lasers are real, they could reveal new insights into how energy is generated in the most extreme environments in the universe. This could have implications for everything from high-energy physics to the development of new technologies. The fact that black holes, objects that are usually considered to be one-way passages to oblivion, might also act as powerful sources of energy could challenge our perceptions of what these cosmic giants are capable of. For instance, could the energy emitted by a black hole laser be harnessed? While this may sound like science fiction, the study of black hole physics often leads to unexpected innovations. In the future, technologies designed to manipulate energy at extreme scales could potentially draw from the principles that govern the behavior of black holes. Though such ideas may seem far off, history has shown that the study of astrophysical phenomena has led to breakthroughs in technology that were once unimaginable. As the study of black holes continues to evolve, the quest for black hole lasers will be a crucial part of that journey. Whether or not we eventually detect black hole lasers, the pursuit of knowledge about these cosmic objects will continue to drive advancements in our understanding of the universe. The mysteries surrounding black holes are vast, and each discovery brings us closer to answering the fundamental questions about the nature of space, time, and the forces that govern the cosmos. In the coming decades, as our observational tools continue to improve and our theoretical models become more sophisticated, the possibility of detecting black hole lasers becomes increasingly plausible. And as we stand at the intersection of quantum mechanics and general relativity, the discovery of such a phenomenon would not only mark a major milestone in astrophysics, but also open new doors to understanding the fundamental nature of the universe itself. The journey to uncover the truth about black hole lasers is one that will inspire generations of scientists, thinkers, and explorers to continue pushing the boundaries of human knowledge and understanding. The notion of black hole lasers captures the imagination because it represents the ultimate convergence of two of the most powerful forces in the universe, gravity and quantum mechanics. The combination of these two realms, so different in nature, could potentially lead to new insights into how the universe operates on both the largest and smallest scales. As we continue to probe deeper into the heart of black holes, the idea of laser-like radiation emerging from these enigmatic objects could offer us a glimpse into previously uncharted territories of physics. One of the key challenges when discussing black hole lasers is understanding the incredibly high energies involved. Black holes themselves are extraordinary objects that concentrate vast amounts of mass and energy in a tiny space. The gravitational pull near a black hole is so strong that it distorts the fabric of spacetime itself, creating a region from which nothing, not even light, can escape once it crosses the event horizon. However, before an object crosses this boundary, the interactions between matter, light, and the quantum fields around the black hole are complex and diverse. As black holes spin and accrete matter, they generate a variety of energetic phenomena, including intense radiation. Some of this radiation can be the result of the black hole interacting with surrounding fields, such as the electromagnetic field. In this scenario, the concept of black hole laser suggests that under certain conditions, this radiation could become coherent, or organized in a way that produces a directed beam of energy, similar to the focused light produced by a laser on Earth. This process would require a delicate balance of factors, including the black hole's rotation, the nature of the surrounding quantum fields, and the presence of specific wave-like phenomena like superradiance. Superradiance is particularly interesting because it provides a mechanism by which energy can be extracted from a rotating black hole. In superradiance, waves that interact with a rotating black hole can gain energy and become amplified. This is opposite to what we would expect from regular interactions with matter, where energy is usually absorbed or dissipated. If certain conditions are met, these amplified waves could potentially form coherent beams of radiation. This phenomenon has already been studied in a variety of contexts, such as in systems involving rotating black holes or Bose-Einstein condensates, where superradiance leads to the amplification of waves. This process could, in theory, generate highly organized radiation in a manner similar to a laser. For a black hole laser to exist, however, a number of key elements need to be in place. One of the primary considerations is the nature of the waves or fields involved. In the case of a black hole, the waves could be gravitational waves, electromagnetic waves, or even other types of quantum fields. The exact type of wave needed for a black hole to produce a coherent beam of radiation is still a topic of active research. In order to produce a laser-like effect, the wave must not only be amplified but also become coherent over a significant distance. To achieve this, the black hole must rotate rapidly enough to allow superradiance to take place. The faster the black hole spins, the greater the likelihood that the waves interacting with it will experience superradiance. In addition, the wave must be properly tuned to match the black hole's frequency. This is where the unique properties of black holes come into play. The exact conditions required for the generation of a black hole laser depend heavily on the specific characteristics of the black hole, such as its mass, spin, and charge, as well as the surrounding environment. For instance, the interaction between the black hole's strong magnetic field and the plasma surrounding it could play a crucial role in shaping the radiation that is emitted. Theoretical models of black hole lasers also take into account the role of the event horizon in shaping the behavior of radiation. The event horizon is the boundary beyond which nothing can escape the black hole's gravitational pull, not even light. However, before an object or wave crosses the event horizon, the intense gravitational field can cause dramatic changes in the behavior of radiation. In some models, it is suggested that the radiation could be amplified as it spirals around the black hole, gaining energy before it is emitted in a coherent beam. This process would require precise conditions, but it could theoretically explain how black holes might produce laser-like radiation. In the broader context of theoretical astrophysics, black hole lasers offer a fascinating avenue of exploration. They present the possibility of using black holes as natural amplifiers of energy, something that could revolutionize our understanding of energy production in the cosmos. While we are far from being able to harness black hole lasers for practical use, the study of such phenomena could lead to breakthroughs in our understanding of how energy and matter interact under extreme conditions. To detect black hole lasers, astronomers would need to observe the radiation emitted by black holes with an unprecedented level of sensitivity. Current telescopes and observatories, such as the Event Horizon Telescope, have already provided us with stunning images of black holes, but detecting the faint, coherent emissions that might come from a black hole laser would require even more advanced technology. The search for such radiation would also require careful modeling to distinguish it from other types of emissions, such as the chaotic radiation typically emitted by accretion disks or relativistic jets. In addition to direct observation, researchers are also exploring the theoretical consequences of black hole lasers on the larger scale of astrophysical processes. For example, if black hole lasers are possible, what does this mean for the environment around black holes? Could the emission of coherent radiation from a black hole influence the behavior of nearby stars or galaxies? Could these emissions affect the dynamics of black hole mergers, or alter the way we think about the role of black holes in the evolution of the universe? These are some of the questions that arise when considering the potential impact of black hole lasers on our understanding of cosmic events. In the quest to answer these questions, the theoretical study of black hole lasers also touches on some of the most fundamental issues in physics, particularly the quest to unify general relativity and quantum mechanics. Black hole lasers, if they exist, would represent a direct manifestation of quantum effects in the most extreme gravitational environments. Understanding how quantum fields behave near the event horizon of a black hole would offer new insights into the nature of spacetime, gravity, and quantum fields. This could provide the key to unlocking some of the most profound mysteries of the universe, from the nature of dark matter and dark energy to the ultimate fate of the cosmos. As we look to the future of black hole research, the possibility of black hole lasers offers an exciting frontier for scientific discovery. The combination of theoretical modeling, advanced observational techniques, and the ongoing exploration of quantum gravity could eventually bring us closer to understanding whether black hole lasers are real phenomena or merely an intriguing theoretical possibility. Either way, the pursuit of knowledge about these extraordinary objects continues to drive the field of astrophysics forward, challenging our understanding of the universe and the laws that govern it. In the coming decades, as our tools for observing the universe become more powerful and our theoretical models more sophisticated, we may uncover new evidence that helps confirm or refute the existence of black hole lasers. If we do, it would mark a significant milestone in our exploration of the most extreme environments in the universe. Whether or not black hole lasers are discovered, the search for them will continue to push the boundaries of what we know about black holes, quantum mechanics, and the nature of reality itself. As our technology improves, we may be able to uncover more clues that could shed light on the mysterious nature of black hole lasers. One area where advancements in both theory and observational techniques are likely to intersect is in the development of quantum telescopes, or new sensors capable of detecting the minute and subtle radiation that might emerge from these cosmic giants. The key challenge here will be isolating the specific signatures of coherent radiation from the much stronger, and often more chaotic, emissions that typically surround black holes. Researchers are already working on some of the most sensitive instruments in existence to capture the faintest signals in space. For example, observatories like the Laser Interferometer Gravitational Wave Observatory, LIGO, have provided us with groundbreaking observations of gravitational waves, and the next generation of such detectors will likely improve our ability to observe quantum phenomena in extreme environments. LIGO and similar observatories could, in theory, be adapted to detect the kind of gravitational wave signatures that might accompany black hole laser emissions, offering a new way to probe the intense environments surrounding these objects. Another possible avenue for the detection of black hole lasers could come from the study of gravitational lensing. Gravitational lensing occurs when the light from distant objects, such as stars or galaxies, is bent by the gravitational field of a massive object, such as a black hole. This effect allows us to study objects that would otherwise be obscured by the black hole's event horizon. If black hole lasers exist, it's conceivable that their radiation could be bent and distorted in a way that would allow us to detect them from across vast distances. Gravitational lensing could therefore provide a natural tool for astronomers to look for the subtle, focused beams of radiation that might emerge from a black hole laser. While we are still a long way from confirming the existence of black hole lasers, their potential implications extend far beyond astrophysical research. The study of black hole lasers could influence other fields of physics as well, including quantum field theory and high-energy particle physics. Understanding how quantum fields behave in the extreme environment near a black hole could help us test the limits of current physical theories and possibly reveal new insights into the nature of space-time and gravity. For instance, black holes themselves are still a mystery in many ways. While we understand their fundamental characteristics, such as their event horizon, singularity, and immense gravitational pull, there are still many unanswered questions about how they behave under extreme conditions. If black hole lasers were found to exist, they would open new doors for understanding how matter and energy behave in such a high-energy, quantum gravitational environment. This could help us refine our understanding of general relativity, quantum mechanics, and possibly even lead to the discovery of new physical principles. The idea that black holes could potentially serve as natural sources of coherent radiation could also have implications for our understanding of the fundamental forces of nature. For example, a black hole laser might provide a new way to explore the relationship between electromagnetic fields and gravitational fields. By observing how the two forces interact in the presence of a black hole, scientists could gain insight into how gravity works on quantum scales, a long-standing puzzle in physics. Such a breakthrough could eventually contribute to the quest for a unified theory of everything, where all fundamental forces are reconciled into a single framework. The concept of black hole lasers also intersects with the study of black hole information paradox and the holographic principle. According to the holographic principle, information that falls into a black hole is not lost, but rather encoded on the event horizon in a two-dimensional form. If black hole lasers exist, they could provide an experimental way to test this principle by showing how information or energy might escape from a black hole in a coherent, laser-like manner. The detection of such radiation could offer a direct probe into how quantum information behaves in the presence of extreme gravitational fields, potentially unlocking secrets about the fabric of reality itself. One of the most exciting aspects of the search for black hole lasers is the potential for new discoveries that could fundamentally alter our understanding of the universe. If we are able to detect and study these lasers, it would not only deepen our understanding of black holes, but could also reveal new processes or phenomena previously unknown to science. It might even lead to the development of entirely new technologies or applications, such as the use of black hole lasers in space exploration or energy production, although these possibilities are still far from realization. Additionally, the study of black hole lasers might inspire us to rethink how we approach space exploration. Understanding the nature of black holes and their extreme environments could help us design better instruments for observing the cosmos, improve our ability to detect high-energy events, and provide new insights into how stars and galaxies evolve. With future advancements in observational technology, we may be able to create a clearer picture of the role black holes play in the larger cosmic landscape, and how they might influence the formation and evolution of galaxies, stars, and other celestial bodies. As we continue to explore the nature of black holes and the potential for black hole lasers, we must also acknowledge that there is still much we don't know. The conditions near a black hole are so extreme that they push the limits of our current understanding of physics. However, as our theoretical models evolve and our observational tools improve, we may one day be able to confirm or disprove the existence of black hole lasers. In the meantime, the study of these theoretical phenomena continues to push the boundaries of scientific inquiry. Each new discovery, whether related to black holes, quantum fields, or the behavior of light and radiation under extreme conditions, brings us one step closer to unraveling the mysteries of the universe. Even if black hole lasers are never directly observed, the process of searching for them may lead to other, unexpected discoveries that will shape our understanding of the cosmos for generations to come. Through all of this, one thing is certain: the study of black hole lasers will continue to be a fascinating and challenging pursuit for physicists, astronomers, and anyone with a curiosity about the universe. Whether or not they exist, the very idea of black holes acting as natural lasers forces us to reconsider what we know about the universe and the forces that govern it. As we continue to probe deeper into the nature of black holes and their interactions with quantum fields, the possibility of uncovering black hole lasers could provide new ways to explore the most mysterious and extreme environments in the universe. In continuing the journey into the realm of black hole lasers, it's important to appreciate the broader context in which such a phenomenon could potentially reshape the way we think about the fundamental forces of nature. For centuries, black holes were seen as strange objects that defied conventional understanding. Their massive gravitational pull was thought to be so intense that not even light could escape from within the event horizon. This idea, first proposed by John Michell in the 18th century, eventually became a cornerstone of general relativity with Albert Einstein's groundbreaking theories. However, despite their long-standing recognition in physics, black holes are still surrounded by many unanswered questions. The concept of black hole lasers pushes the boundaries of this understanding, offering a way to imagine black holes not just as traps of matter and energy, but as potential sources of highly coherent radiation. If these lasers were real, it would imply that black holes could emit energy in a manner similar to man-made lasers, where photons are amplified and focused into narrow beams. This challenges our traditional view of black holes as purely destructive forces and opens the possibility of them being sources of organized, structured radiation. One of the most exciting things about the idea of black hole lasers is the potential it has to connect several fields of physics. First, the quantum field theory is critical in understanding the behavior of particles and fields at the smallest scales. The strong electromagnetic fields near black holes could provide a natural laboratory for studying the quantum properties of light and matter in extreme environments. The role of virtual particles, Hawking radiation, and quantum fluctuations near a black hole could play a pivotal part in generating these hypothetical laser emissions. Understanding how quantum fields behave near these objects could give us a clearer picture of how they interact with gravity, and how those interactions might produce coherent radiation. Moreover, the study of black hole lasers intersects with cosmology, the study of the universe as a whole. Black holes are fundamental objects in cosmology, and their influence can be felt at every level of cosmic structure, from the formation of galaxies to the behavior of large-scale structures in the universe. If black holes can emit laser-like radiation, it could offer new insights into how galaxies and stars form and evolve, as the energy from these emissions might interact with surrounding matter in ways that influence the growth of galactic structures. Understanding the potential of black hole lasers to release highly focused beams of energy could change the way we view the energy dynamics in the most distant regions of the universe. In terms of direct applications, black hole lasers could revolutionize energy production and communication technologies. Imagine harnessing the power of a black hole's intense electromagnetic fields to generate usable energy. While the technology to capture and manipulate black hole radiation is still firmly in the realm of science fiction, the theoretical implications are worth considering. If such a source of coherent radiation could be controlled, it might offer a new form of energy generation, albeit far beyond our current capabilities. The challenge would lie in designing technology that could withstand the intense gravitational forces and radiation that black holes exert, but with time and innovation, these limitations may one day be overcome. Furthermore, in a more speculative sense, black hole lasers could have profound implications for the way we think about interstellar communication. Since black holes are scattered throughout the cosmos and they can emit energy in the form of radiation, they could theoretically act as natural beacons. Such a signal could potentially be used to communicate across vast distances, providing a new avenue for sending information from one part of the galaxy to another. The high energy and focus of black hole radiation could allow for the transmission of information with unprecedented efficiency. Though this idea remains firmly in the realm of theory, it's another example of how a deeper understanding of black holes could change the way we interact with the cosmos. The theoretical framework for black hole lasers also forces us to reevaluate the very fabric of space-time itself. Einstein's theory of general relativity has been the bedrock of modern physics for over a century, but black hole lasers, if they exist, could provide new avenues for testing this theory under extreme conditions. For example, the existence of coherent radiation from a black hole could help us test the limits of the space-time curvature near the event horizon, shedding light on how space-time behaves when subjected to immense gravitational and electromagnetic forces. Such insights could eventually lead to a better understanding of the nature of gravity on quantum scales and even provide the missing pieces to form a unified theory of quantum gravity. At the same time, these theoretical black hole lasers could offer new avenues for exploring one of the most intriguing aspects of black holes: their role in the fate of information. The black hole information paradox, which posits that information entering a black hole might be lost forever, has been one of the biggest challenges in theoretical physics. If black hole lasers were real, their radiation could serve as a new form of information retrieval, where energy or data could escape from a black hole in an organized, structured form. This would offer a direct test of some of the most profound ideas in quantum mechanics and general relativity, providing crucial clues about the true nature of the event horizon and the fate of information trapped within black holes. As we venture further into the theoretical study of black hole lasers, it's important to consider the broader context of scientific progress. Many great discoveries in physics have emerged from the study of objects and phenomena that were once considered too far out of reach. The early study of black holes was, in many ways, a leap of faith, an attempt to understand the unknown forces governing the universe. The concept of black hole lasers could, in a similar way, push our understanding of spacetime and quantum mechanics in entirely new directions. While it may take decades or even centuries for us to confirm the existence of black hole lasers, the pursuit itself will likely yield numerous breakthroughs in our understanding of the universe. In essence, the search for black hole lasers is not just about confirming the existence of a single phenomenon, but is a step toward understanding the deeper mysteries of the cosmos. Each theoretical breakthrough, each new model or piece of observational evidence, brings us closer to understanding the true nature of black holes and the forces that govern them. Whether or not black hole lasers turn out to be real, the quest to understand them will undoubtedly lead to new discoveries in physics, astronomy, and our broader understanding of the universe. As we continue to delve deeper into the potential reality of black hole lasers, we find that the implications extend far beyond the realm of purely theoretical physics. At their core, these lasers could represent a bridge between some of the most perplexing paradoxes of modern physics, offering a way to test and refine the theories that have shaped our understanding of the universe. In many ways, the study of black hole lasers encapsulates the spirit of scientific inquiry, an ongoing journey to push the boundaries of what we know and imagine the possibilities that could lie just beyond the horizon. The idea of black hole lasers is closely tied to the concept of Hawking radiation, a theory proposed by physicist Stephen Hawking in 1974. According to this theory, black holes are not completely black, but instead emit radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, is produced when virtual particle pairs pop in and out of existence near the event horizon. One particle in the pair falls into the black hole, while the other escapes, creating the appearance of radiation coming from the black hole. This groundbreaking concept challenged the conventional view of black holes as perfect absorbers of matter and energy, and instead opened the door to the idea that they might actually emit energy in a controlled manner. In the case of black hole lasers, the idea would be that the radiation escaping from the black hole could be amplified and focused into a highly coherent beam, much like the way lasers work on Earth. To understand how this could occur, it's important to examine the conditions near a black hole and the interactions between gravity, electromagnetic fields, and quantum fluctuations. One crucial factor in the potential development of black hole lasers is the role of electromagnetic fields. Near a black hole, the intense gravitational pull creates a highly curved spacetime that can bend light and other forms of radiation. In certain circumstances, these gravitational fields could interact with the electromagnetic fields in such a way that energy becomes concentrated, leading to the formation of a coherent beam of radiation. This beam could, in theory, have properties similar to those of a laser, including narrow focus, high intensity, and the ability to travel over vast distances without losing much energy. For this to occur, however, there are several complex conditions that must be met. First, the interaction between the gravitational field and the electromagnetic field must be strong enough to produce a significant amount of energy. Second, the quantum fluctuations that generate Hawking radiation must be amplified to the point where they can coherently escape the black hole. The process would likely involve a combination of quantum mechanics, general relativity, and electromagnetism, three areas of physics that have yet to be fully unified into a single framework. The idea of black hole lasers also brings us back to the concept of event horizons. These boundaries mark the point beyond which nothing, not even light, can escape the black hole's gravitational pull. In theory, the event horizon acts as a one-way gate, allowing matter and energy to fall in but not return. However, black hole lasers would require a rethinking of the event horizon's properties. Instead of being a complete barrier, the event horizon in this context might act as a semi-permeable boundary, allowing certain forms of radiation to escape under specific conditions. This concept is similar to the way that lasers on Earth are constructed. In conventional lasers, a population of particles, such as atoms or molecules, is excited by an external energy source, causing them to emit photons in a coherent and amplified manner. The photons bounce back and forth between mirrors, increasing in intensity, until they are finally released as a focused beam of light. In the case of black hole lasers, the energy source would be the black hole's intense gravitational and electromagnetic fields, while the photons would be the Hawking radiation that is generated near the event horizon. The theoretical concept of black hole lasers also intersects with another fascinating area of physics: quantum information theory. The study of information in quantum systems has revolutionized our understanding of how data is processed and transmitted on the smallest scales. In particular, the so-called quantum information paradox raises profound questions about the nature of information in the universe, especially when it comes to black holes. If black holes can emit coherent radiation in the form of a laser, it might provide a way to extract and store information that was previously thought to be lost forever inside the black hole. This idea has major implications for our understanding of the fundamental laws of physics. The black hole information paradox is one of the most significant unresolved issues in modern theoretical physics, and the potential existence of black hole lasers could offer new insights into how information behaves under extreme gravitational conditions. If black holes can emit laser-like radiation that carries information, it might help to resolve the paradox by suggesting that information is not lost inside the black hole, but instead is encoded in the radiation that escapes. Moreover, black hole lasers could also offer insights into the mysterious nature of dark matter and dark energy. These elusive components of the universe are thought to make up the majority of the cosmos, yet they remain largely invisible and undetectable through conventional methods. If black holes can emit highly focused beams of radiation, they could potentially interact with dark matter and dark energy in ways that we are only beginning to understand. The energy released by black hole lasers might provide a new tool for studying the properties of these mysterious substances, potentially unlocking some of the deepest secrets of the universe. As with any groundbreaking scientific theory, the idea of black hole lasers is still in its infancy. Much more work needs to be done to understand the precise mechanisms that could allow for such a phenomenon to occur. For example, scientists would need to develop sophisticated models to describe the interactions between black holes, electromagnetic fields, and quantum fluctuations in a way that is consistent with both general relativity and quantum mechanics. Current technology is far from being able to directly observe black hole lasers, but with future advancements in telescopes and observational techniques, we may one day be able to detect the telltale signs of coherent radiation escaping from a black hole. In the meantime, the theoretical exploration of black hole lasers serves as a testament to the power of human curiosity and ingenuity. It reminds us that even the most enigmatic and seemingly destructive objects in the universe, such as black holes, may hold the key to some of the most profound mysteries of the cosmos. Whether or not black hole lasers turn out to be a real phenomenon, the pursuit of understanding them will undoubtedly lead to new discoveries that could reshape our view of the universe and our place within it. In the presence of a strong gravitational field, such as that near the event horizon of a black hole, quantum field effects become significantly pronounced. This intense curvature of spacetime alters the vacuum state itself, creating a situation where virtual particles can gain enough energy to become real. When these quantum fluctuations interact with powerful electromagnetic fields, especially in the case of rotating or charged black holes, new dynamics can emerge. It is within this context that theorists propose the possibility of stimulated emission processes, similar in essence to how traditional lasers work. To visualize this, imagine a rotating black hole, what physicists refer to as a curved black hole. Due to its rotation, such a black hole can possess an ergosphere, a region outside the event horizon where space itself is dragged along with the black hole's spin. Inside this ergosphere, particles and radiation can actually extract energy from the black hole, a concept known as the Penrose process. When electromagnetic waves enter this region under certain conditions, they can be amplified. This is the foundation of what's known as superradiance, and it is a key ingredient in the theoretical model of a black hole laser. Superradiance, when combined with a reflective boundary, like a mirror surrounding the black hole or an effective trapping region formed by spacetime geometry, could in theory lead to repeated amplification of these waves. Each pass would intensify the radiation, just like light bouncing between mirrors in a traditional laser cavity. This self-amplifying feedback loop, predicted by some models, would ultimately produce an intense, coherent beam of energy, a black hole laser. One particularly interesting concept involves placing the black hole within a sort of mirror box, not literally, but mathematically, using a surrounding environment that causes certain wavelengths of radiation to reflect back toward the ergosphere. This setup, proposed in theoretical models, turns the black hole into a cosmic-scale optical cavity. Waves bouncing between the black hole and this effective mirror would undergo repeated rounds of superradiant amplification. Over time, this could create conditions ripe for lasing. What's even more fascinating is the potential energy output. The rotational energy of a black hole is staggering, and even a small fraction of it being extracted and amplified in this way would produce phenomenal emissions, far surpassing the output of any star or typical astrophysical process. These beams could theoretically traverse vast stretches of the cosmos, possibly explaining some high-energy astrophysical phenomena that remain mysterious today. The energy source for this process, the black hole's spin, acts like the pump in a traditional laser, constantly feeding energy into the system. As long as the rotation continues and the cavity conditions are maintained, the black hole laser could persist, pumping out coherent energy beams in defiance of our classical expectations. This raises an intriguing question: could these coherent beams be observable? Might some of the unexplained gamma-ray bursts or other energetic phenomena be signatures of such a process? The difficulty lies in distinguishing coherent radiation produced by black hole lasers from the chaos of other high-energy emissions in the universe. However, theoretical physicists continue to refine models that might predict distinctive signatures, patterns in the frequency, polarization, or timing of the radiation that could serve as telltale signs. At the core of all this lies an even deeper mystery. If black hole lasers do exist, they not only challenge our understanding of black holes but also push us toward a more unified view of the universe, one where gravity, electromagnetism, and quantum mechanics don't merely coexist, but actively interact in elegant and complex ways. In effect, this creates a cosmic resonant cavity. With every pass, low-frequency waves gain more energy due to superradiant scattering off the rotating black hole, eventually forming a beam of amplified radiation, a theoretical laser emerging from the most extreme object in the universe. While this sounds like pure science fiction, the mathematics supporting the possibility of black hole lasers is grounded in legitimate physical theory, combining aspects of general relativity, quantum field theory, and thermodynamics. The notion of a black hole bomb, which is closely related to black hole lasers, illustrates how energy amplification could become catastrophic under the right conditions. If a massive, spinning black hole is surrounded by a perfectly reflecting mirror, any incident wave can bounce back and forth between the black hole and the mirror. Each time it reflects off the black hole's ergosphere, it gains more energy due to superradiance. Eventually, the energy builds up exponentially, leading to a potentially explosive release of radiation. Replace the bomb with controlled partial mirrors or effective trapping regions, and you get a black hole laser, coherent, directed, and immensely powerful. The mechanism is still purely theoretical, but analog models on Earth have allowed physicists to simulate some of these effects in controlled environments. For example, in Bose-Einstein condensates, ultra-cold states of matter where particles behave like waves, researchers have simulated horizons that mimic the event horizon of a black hole. In these systems, sound waves rather than light waves are used, and a form of sonic Hawking radiation has been observed. These analog black holes offer a tantalizing glimpse into the physics that might govern real black hole lasers, allowing scientists to test ideas without needing to get close to an actual black hole. One particularly interesting aspect of these analog models is that they reinforce the idea that event horizons don't necessarily have to be gravitational. They can emerge from any system where waves are prevented from escaping a region due to a change in the properties of the medium, like a shift in the speed of sound or light. In this way, experimental physicists have turned their attention to fluid dynamics, optics, and condensed matter systems to replicate some of the exotic phenomena thought to occur near black holes, including the kind of feedback loops necessary for laser-like emissions. If black hole lasers do exist in nature, their observational signature would be unlike anything we've seen before. Traditional black holes are detectable via the radiation emitted from their accretion disks or the gravitational waves they produce when they merge. But a black hole laser could produce periodic, coherent bursts of radiation, potentially even observable across interstellar or intergalactic distances. Depending on the frequency and intensity, these beams could pierce through vast stretches of space, carrying with them the fingerprints of the extreme conditions from which they emerged. Some scientists speculate that fast radio bursts, FRBs, mysterious and intense pulses of radio waves coming from distant galaxies, could be related to phenomena like black hole lasers or other forms of superradiance. While there is no conclusive evidence yet linking FRBs to such exotic processes, the hypothesis remains on the table due to the unexplained nature and power of these bursts. If we ever do detect a signature consistent with coherent amplification from a black hole, it would revolutionize our understanding of not just black holes, but the fundamental physics of the universe. A further layer of intrigue is added when we consider the role of quantum information in black hole lasers. One of the great puzzles in modern physics is the black hole information paradox. How information that falls into a black hole could possibly be preserved or retrieved if the black hole eventually evaporates. If Hawking radiation is truly random, as once proposed, it seems to destroy information, violating the principles of quantum mechanics. But if black hole lasers are real, and if they involve coherent emissions tied to the structure of spacetime and field interactions, they might offer a channel for information to be preserved or even extracted from the black hole over time. This hints at a deeper connection between quantum mechanics and gravity, something that physicists have long sought in the form of a unified theory. Black hole lasers, if ever detected, could serve as natural laboratories for testing these unified theories. Their study may help bridge the gap between the macroscopic world governed by general relativity and the microscopic domain dominated by quantum mechanics. The theoretical modeling required to simulate black hole lasers often involves advanced concepts from quantum gravity, including string theory and loop quantum gravity, both of which attempt to reconcile these two major frameworks of physics. Moreover, the concept touches on thermodynamics in profound ways. Black holes are known to obey laws analogous to the laws of thermodynamics, possessing entropy, temperature, and the ability to exchange energy. If black hole lasers emit coherent radiation, then we may need to redefine or expand the current understanding of black hole thermodynamics to account for directed energy output. This raises compelling questions about the entropy of black hole systems, the nature of time reversibility, and the flow of energy in extreme gravitational regimes. One also has to consider how stable such black hole laser configurations would be. In theory, a black hole laser powered by superradiance could keep building up energy until it reaches a critical point, either blowing apart its own amplification structure or causing rapid mass loss from the black hole. Alternatively, there could be natural self-regulating mechanisms that keep the amplification in check, much like gain saturation in conventional lasers. These are complex questions that are difficult to answer without more precise models and, ideally, observational data. Another fascinating avenue of research concerns whether black hole lasers could ever be created artificially. Though wildly speculative, some theoretical physicists entertain the idea that an advanced civilization could manipulate spacetime to generate stable, small-scale black holes and use them as energy sources, or even as communication beacons. The coherent radiation of a black hole laser could, in principle, transmit information across the galaxy with minimal dispersion. This idea connects with the broader field of astroengineering and SETI, search for extraterrestrial intelligence, where researchers look for technosignatures, indicators of intelligent life capable of manipulating cosmic phenomena. From a cosmological perspective, black hole lasers might have even played a role in the early universe. If primordial black holes formed during the chaotic conditions after the Big Bang, and if some of them had the right spin and environmental conditions, it's possible they could have emitted bursts of amplified radiation. These early cosmic lasers might have contributed to reionization, seeded structure formation, or even left detectable imprints in the cosmic microwave background. Though this remains speculative, it's a reminder of how theoretical constructs can sometimes shed light on deep questions about our origins. These analog experiments suggest that the bizarre physics predicted near black holes might not just be theoretical curiosities. They may be real, tangible processes that could eventually be observed in the cosmos. The prospect of naturally occurring black hole lasers opens up a range of speculative but scientifically grounded questions. Could some of the unexplained cosmic phenomena we've detected be related to such processes? Might we one day identify unique signals, intense, highly coherent emissions, that point directly to black hole laser activity? One particularly intriguing implication of black hole lasers involves their potential as beacons across vast cosmic distances. Coherent radiation is more focused and carries more information than random emissions. If a black hole laser were to exist naturally, its beam might be visible across galaxies, acting as a sort of cosmic lighthouse. In fact, this idea has prompted some to suggest that we might confuse such emissions with other highly energetic phenomena like gamma ray bursts or fast radio bursts, signals we still don't fully understand. The emission of coherent radiation from black holes also raises fascinating questions about the fundamental limits of energy extraction from gravity. Stephen Hawking's theoretical prediction of black hole evaporation through Hawking radiation implies that black holes slowly lose mass over time by radiating away energy. Black hole lasers, through the mechanism of superradiance, represent a different kind of energy leak, one that's much more rapid and possibly far more dramatic under the right conditions. This mechanism could significantly alter a black hole's mass and angular momentum, introducing a dynamical evolution that differs from standard models. Superradiant instabilities could, in principle, limit the spin of black holes. If black holes spin too fast, they might begin to shed their rotational energy through the creation of these laser-like emissions. This introduces the idea of a natural upper bound to a black hole's angular momentum, not just because of structural instability, but because the universe itself prefers to prevent runaway spinning by creating mechanisms to bleed off energy. And then there's the possibility of exotic particles playing a role in this grand cosmic play. If ultralight bosons exist, a hypothetical class of particles that includes candidates for dark matter, they could form clouds around rotating black holes. These clouds would grow through superradiant amplification, feeding off the black hole's spin and potentially forming oscillating fields capable of radiating energy in structured, coherent ways. Some theories suggest that such clouds could last for eons and might even interact with gravitational waves, distorting spacetime in detectable patterns. In recent years, gravitational wave observatories like LIGO and Virgo have opened a new window into the behavior of black holes. These instruments have detected the mergers of massive black holes, providing unprecedented insights into their dynamics. Some physicists speculate that if black hole lasers or superradiant clouds exist, they might leave subtle fingerprints in the gravitational wave signals we receive. Variations in spin-down rates, modulations in waveform patterns, or unexpected echoes might all hint at exotic amplification processes occurring in regions we've only begun to understand. On the observational front, the Event Horizon Telescope's imaging of the black hole in M87 offered humanity its first direct glimpse of a black hole's shadow. While the image didn't reveal any laser-like beams, it demonstrated that we can resolve features near the event horizon with increasing precision. Future generations of telescopes might be able to look for narrow jets or structured emissions that could suggest the presence of coherent amplification mechanisms. Even more compelling is the idea that black hole lasers could play a role in shaping the energetic structure of galaxies. Supermassive black holes at galactic centers often emit powerful jets of relativistic particles, stretching across light years. While these jets are usually attributed to magnetic interactions in the accretion disk, the possibility that some form of coherent radiation, perhaps even laser-like, might be involved has not been fully ruled out. If black hole lasers can exist, they may contribute to the stability, shape, or propagation of these immense jets. One challenge that remains is the lack of direct observational signatures unique to black hole lasers. In a universe filled with chaotic, high-energy events, distinguishing a coherent beam generated by superradiant amplification from standard emissions is no small feat, but as instrumentation improves, the search continues for unique polarization patterns, frequency harmonics, or angular collimation that might betray the presence of a cosmic-scale laser. The theoretical backing continues to grow stronger. Mathematical models now incorporate rotating geometries, massless and massive fields, and nonlinear feedback loops to simulate potential behaviors of black hole lasers. Some simulations even suggest ringing effects, quasi-periodic emissions that build up and fade in regular cycles, an echo of traditional lasers, but born from warped spacetime rather than engineered optics. And as with many theoretical breakthroughs, the idea of a black hole laser continues to push the boundary between science and speculation. The deeper we peer into the fundamental laws of nature, the more we discover that phenomena once confined to science fiction may have a place in the realm of physical possibility. A black hole laser might never be something we can build, but it could be something we witness. If such an object is ever confirmed, it would mark not only a triumph of theoretical physics, but a profound extension of human understanding. To gaze into the heart of a black hole and see a beam of structured, coherent radiation emerging from it would not just be an observation. It would be a cosmic message, one that tells us our universe is far more strange, elegant, and layered than we ever imagined. Moreover, the potential for black hole lasers to influence cosmic evolution introduces an entire frontier of theoretical astrophysics. If such lasers indeed operate in nature, they could affect their local environments dramatically. The intense, focused energy could heat surrounding gas clouds, alter star formation rates, or even drive relativistic jets. These emissions could act as feedback mechanisms that influence the development of galaxies, much like how active galactic nuclei regulate the growth of their host galaxies through energy output. Another fascinating implication involves the detectability of black hole lasers. Unlike traditional black holes, which are notoriously difficult to observe directly due to their nature as light-trapping objects, a black hole laser would generate coherent, detectable emissions. These emissions could stand out from background radiation due to their frequency, directionality, and coherence. If astrophysical surveys are refined to search for such signatures, we might one day spot one, perhaps even retroactively identifying one in archived data from space telescopes or radio arrays. Interestingly, some researchers have proposed that black hole lasers could occur in systems involving ultralight particles like axions. These hypothetical particles arise in various extensions of the standard model of particle physics, and could solve some enduring mysteries, such as the nature of dark matter. In scenarios where axions surround a rotating black hole, they can become trapped in quasi-bound states, gradually extracting energy via superradiance. These axion clouds could grow to immense sizes and eventually annihilate to produce detectable radiation, effectively forming a kind of black hole laser driven by exotic matter. This theoretical setup is especially exciting because it presents a possible bridge between gravitational wave astronomy and particle physics. If such systems exist, their dynamics could emit gravitational waves at highly specific, narrow frequencies, signals we might eventually detect with advanced interferometers like LIGO, Virgo, or the future space-based LISA mission. In other words, black hole lasers might not only shine with electromagnetic light but also sing in gravitational waves. At this point, we enter a realm where observational signatures become crucial. Distinguishing a true black hole laser from other high-energy astrophysical events would require not just detection of emissions but correlation across different forms of radiation. A multi-messenger approach, observing the same event through both light and gravitational waves, could serve as the ultimate confirmation. A black hole that simultaneously produces a coherent gamma-ray burst and a continuous gravitational wave at a predicted frequency would strongly support the existence of this phenomenon. Furthermore, the theoretical structure of black hole lasers invites deeper exploration into the fabric of spacetime itself. The interactions between event horizons, quantum fields, and rotation stretch our current understanding of physics to its limits. Could black hole lasers offer insights into the long-sought unification of general relativity and quantum mechanics? Could they reveal hidden features of spacetime curvature or quantum entanglement near extreme gravitational boundaries? Some speculative theories even suggest that black hole lasers could play a role in the information paradox. The paradox arises from the apparent contradiction between Hawking radiation, which seems to erase information about matter falling into a black hole, and quantum mechanics, which forbids information destruction. If energy and information are ejected from black holes in coherent forms, like through laser-like radiation, perhaps the information is preserved after all. This remains highly theoretical, but it hints at deeper connections that might resolve some of the most perplexing questions in modern physics. On the cosmological scale, one might wonder whether black hole lasers have influenced the early universe. During the universe's first moments, dense and highly energetic regions could have birthed primordial black holes with the right conditions for superradiant amplification. If so, these miniature black hole lasers could have contributed to reheating processes, radiation fields, or even influenced the distribution of matter in the cosmic web. It's a speculative idea, but one worth considering as we continue to gather more precise data from the early universe. On a more philosophical level, black hole lasers challenge our intuitions about what nature is capable of. They represent a kind of cosmic machinery, using only space-time geometry, gravity, and wave mechanics, to produce an output akin to human-engineered technology. If nature can build a laser out of a spinning, collapsing star, what else might be possible in the extremes of the cosmos? It reminds us that the universe isn't just a passive backdrop for physics, it's an active, evolving system with mechanisms we are only beginning to understand. In the search for extraterrestrial intelligence, the idea of black hole lasers has even been raised as a potential technosignature. If an advanced civilization understood how to manipulate black holes and superradiant amplification, they might engineer such systems to produce detectable signals. These could serve as beacons or communications across interstellar distances, using the coherence and power of gravitational lasers far beyond our current capabilities. From a practical standpoint, we are still far from being able to confirm any of these ideas definitively. The technological and observational challenges are immense. But with each new advance in instrumentation, from more sensitive radio telescopes to next-generation gravitational wave detectors, the horizon of possibility expands. We may not be able to build black hole lasers ourselves, but the universe might already have done so, and we're just starting to listen. If such systems exist, they could emit gravitational waves with highly specific and predictable signatures. These waves would originate from the dynamics of the axion cloud, its oscillations, instabilities, and eventual decay. Detecting such signals would not only confirm the presence of black hole lasers but could also serve as indirect evidence for the existence of axions or other ultralight bosonic particles. This makes black hole lasers a compelling target for next-generation gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, which is designed to be sensitive to low-frequency gravitational waves from massive black hole systems. Furthermore, black hole lasers could shed light on the ultimate fate of information within black holes. The black hole information paradox, one of the greatest unresolved issues in theoretical physics, arises from the question of whether information that falls into a black hole is lost forever. Hawking's original calculations suggested that the radiation emitted by black holes is purely thermal, carrying no information about the matter that was consumed. However, if black hole lasers produce coherent emissions, then this could imply a non-thermal process that carries subtle imprints of the internal structure or history of the black hole, offering a potential clue toward resolving the paradox. The deeper we explore the theoretical underpinnings of black hole lasers, the more we realize that they challenge and enrich our understanding of quantum field theory in curved spacetime. Black holes are not simply endpoints of stellar evolution. They are dynamic entities that interact with their surroundings in complex and often counterintuitive ways. The laser analogy helps make these complex interactions more intuitive, framing them in terms of feedback loops, resonance conditions, and stimulated emissions that are conceptually easier to visualize than pure general relativistic formalism. From a thermodynamic perspective, black hole lasers may also offer new insight into the entropy and temperature of black holes. Hawking's formulation of black hole thermodynamics links entropy to the surface area of the event horizon. If a black hole emits radiation through stimulated emission, rather than spontaneous quantum fluctuations, then this might suggest an additional layer of thermodynamic behavior, perhaps analogous to systems with population inversion and negative temperature distributions. These ideas remain speculative, but they open up a new dimension of inquiry into the statistical mechanics of spacetime. It's also worth considering the role of symmetry in the operation of black hole lasers. Many of the phenomena we're discussing arise specifically in rotating, curved black holes. The axis symmetry and frame dragging effects associated with rotation create the ergoregion, a key player in the process of superradiance. This means that the rotation of spacetime itself is acting as the energy source for the laser-like amplification. In effect, the geometry of spacetime becomes the gain medium for the process, with the vacuum fluctuations or surrounding fields acting as the lasing material. This interplay between geometry and quantum fields is one of the most profound aspects of black hole physics. It suggests that spacetime is not merely a static stage on which physics happens, it is an active participant in the dynamics. Black hole lasers, by leveraging the curvature and rotation of spacetime, illustrate this beautifully. They exemplify how deeply intertwined general relativity and quantum mechanics must be if we are to truly understand the universe. Expanding beyond black holes, the principles underlying black hole lasers may have implications for other astrophysical objects. For instance, certain rotating neutron stars could, under very specific conditions, exhibit analogous amplification phenomena. These would not be black hole lasers in the strictest sense, but the underlying physics, superradiant-like instabilities, could still apply. This broadens the potential scope of laser-like phenomena in the universe and suggests that amplification through space-time geometry may be more common than previously thought. Even in cosmological contexts, the mathematics of black hole lasers might offer insights. Some inflationary models of the early universe involve rapidly expanding spacetimes with horizon-like features. Quantum field fluctuations in such backgrounds can become amplified through mechanisms that bear a strong resemblance to the ones we've discussed. In this way, black hole laser theory might not just tell us about exotic objects in the far reaches of space, it might help us understand the quantum seeds of structure in the universe itself. And then there's the philosophical aspect. The idea that a black hole, a symbol of inescapable darkness and finality, might actually emit focused, powerful radiation due to the quirks of quantum mechanics is both ironic and poetic. It reframes our view of the cosmos, suggesting that even in the most extreme conditions, patterns, order, and even voice can emerge from what we once thought to be void and silence. From a thermodynamic perspective, black hole lasers offer an intriguing twist to the laws that govern black hole entropy and temperature. According to the Bekenstein-Hawking formula, the entropy of a black hole is proportional to the surface area of its event horizon, not its volume, a startling departure from conventional thermodynamic systems. If a black hole can act as a laser, emitting coherent radiation that is stimulated rather than purely spontaneous, it complicates the traditional thermodynamic picture. The process suggests a mechanism through which structured information, like phase, frequency, or angular momentum, could be transferred out of the black hole in a way that's not entirely entropic. This raises questions about the nature of Hawking radiation itself. If under certain conditions a black hole can emit radiation that isn't purely random, perhaps Hawking radiation too has hidden correlations that preserve quantum information. Some theorists believe that the black hole laser concept hints at a deeper unification of quantum mechanics and general relativity, one where spacetime is not just a passive stage but an active participant in the generation and modulation of quantum fields. If such a union is possible, black hole lasers might be the cosmic laboratories that allow us to observe it in action. We also have to consider how the laser-like behavior of black holes can interact with the surrounding spacetime fabric. In classical general relativity, energy and momentum tell spacetime how to curve, and curved spacetime tells matter how to move. But when energy is emitted in concentrated, directional beams, as is the case in a laser, the curvature of spacetime may change dynamically in response. This feedback loop could lead to localized distortions, possibly even amplifying or focusing gravitational waves in much the same way as light is focused by a lens. It's worth speculating whether these gravitationally focused emissions could interact with other black holes or massive bodies in the vicinity. Could a black hole laser, under the right conditions, stimulate emissions in a neighboring black hole? While entirely speculative, such phenomena would create a kind of gravitational chain reaction, a cosmic cascade, of energy emissions rippling through black hole networks in a galaxy or even across intergalactic distances. What also makes the black hole laser hypothesis so compelling is its accessibility to multiple branches of physics. It's not just a problem for astrophysicists, quantum theorists, string theorists, thermodynamicists, and even condensed matter physicists all have something to contribute. The parallels between the black hole laser model and laboratory analogues of Hawking radiation, like Bose-Einstein condensates or flowing fluids, invite collaborative cross-disciplinary research. It's one of those rare topics where the mathematics of curved spacetime meets the experimental designs of particle accelerators and supercooled atomic traps. Analog black holes, or dumb holes, as they are sometimes cheekily called, simulate event horizons in the lab by creating regions in fluid or optical systems where waves cannot escape. In these setups, physicists have managed to reproduce analogues of Hawking radiation, and some have even proposed designs to mimic black hole laser behavior. While these models lack gravity in the traditional sense, they follow the same mathematical structure. If a black hole laser can be reproduced in a controlled setting, it would provide unprecedented opportunities to study phenomena that are otherwise confined to the most extreme corners of the universe. Even within the confines of Earth, these analogues are teaching us valuable lessons about wave amplification, boundary conditions, and the interplay of quantum fields with horizons. For example, optical fibers have been used to create artificial horizons that mimic the behavior of light near a black hole. Similarly, supersonic flows in fluids can emulate the one-way nature of event horizons. These experiments support the idea that certain behaviors of black holes, once thought to be exotic and unreachable, are actually manifestations of deeper, more universal principles that govern all waves, from light and sound to quantum fields. It's also important to realize that the theoretical foundation for black hole lasers could extend beyond astrophysics and into the realm of quantum computing. If information can be coherently extracted from a black hole-like system, it opens up new possibilities for information storage and transfer at the quantum level. In fact, some researchers have begun to speculate about black hole-inspired quantum devices that leverage similar principles of resonance, coherence, and boundary reflection. While these ideas are still in their infancy, they exemplify how high-level theoretical physics can inspire tangible technological advancements. All of this contributes to a broader philosophical implication, that the universe may be far more interconnected than we imagine. If black hole lasers are real, then every black hole isn't just a passive sink of matter and energy. It becomes an active node in the cosmic web, capable of emitting energy, influencing its environment, and even shaping the behavior of nearby systems. This paints a much more dynamic picture of the cosmos, where the flow of energy and information is more like a symphony than a simple collapse into darkness. As we continue to delve deeper into the concept of black hole lasers, we must address one of the key questions that arises. What do these theoretical phenomena imply for our understanding of the structure and behavior of spacetime itself? Spacetime, as we currently understand it, is a fabric that can bend and stretch under the influence of mass and energy. Black holes, with their extreme gravitational fields, are the ultimate test cases for this theory. The idea that these very objects could potentially act as amplifiers, creating coherent radiation from what we once thought of as the most inhospitable regions of space, challenges our very understanding of the nature of these objects. The emergence of black hole lasers hints that spacetime may have hidden properties that we are only beginning to understand. These lasers operate at the intersection of quantum mechanics and general relativity, where the usual rules break down and strange, unexpected behaviors emerge. Black holes, once considered regions of no return, may hold the key to uncovering new laws of physics. The way in which they interact with quantum fields, and the potential for coherent radiation to be emitted from their proximity, suggests that black holes are not just end states for collapsed stars, but dynamic, active systems that could play a crucial role in the evolution of the cosmos. This shift in perspective opens up a plethora of exciting research avenues. For example, if we are able to detect black hole lasers, it could provide us with a new way of observing the environment around black holes in ways that are completely different from current techniques. Instead of just relying on X-ray emissions or gravitational wave detections to infer the presence of black holes, we could be able to study the feedback loop between the black hole and its environment through the coherent radiation it produces. This could offer a new window into the very mechanics of black hole accretion disks, the interactions between black holes and surrounding matter, and the enigmatic processes that take place inside the event horizon. However, detecting black hole lasers remains an enormous challenge, primarily due to the extreme conditions required for such phenomena to occur. The likelihood of encountering the precise conditions necessary for laser-like amplification, such as an ideal axion cloud, the right amount of rotation and spin, and the appropriate feedback mechanisms, makes these events extremely rare and difficult to observe. Nonetheless, with advancements in observational technologies, such as the Event Horizon Telescope, EHT, and LIGO/Virgo for gravitational wave detection, we may someday be able to observe the faint signals that could be indicative of black hole laser activity. Moreover, these observations may require more than just the sensitivity of our instruments. They may also demand a rethinking of how we approach the analysis of black holes. Current astrophysical models often focus on understanding black holes through the lens of classical general relativity, supplemented with quantum field theories and curved spacetime. But the possibility of black hole lasers introduces the need to incorporate additional complexities, such as nonlinear feedback mechanisms and the influence of novel quantum states like axions or scalar fields, into these models. Incorporating such new theories into our understanding of black holes will also have broader implications for our understanding of quantum gravity. Quantum gravity, which seeks to reconcile the quantum nature of particles with the curved spacetime of general relativity, is one of the most difficult and unresolved areas of modern theoretical physics. The study of black hole lasers, especially in relation to their potential influence on quantum fields, could offer important insights into this elusive theory. If we are able to detect black hole lasers, it would not only confirm that black holes behave in far more complex ways than we currently appreciate, but it could also offer a key to unlocking the long-sought theory of quantum gravity. On a practical level, black hole lasers also raise fascinating possibilities for the manipulation and control of energy. If black holes are indeed capable of producing highly concentrated beams of energy, this raises the tantalizing possibility that future technologies could harness these processes. Of course, this would require an unprecedented level of understanding and control over the behavior of such extreme objects, but the potential applications are limitless. From powering vast interstellar civilizations to enabling new forms of propulsion for space travel, the implications of black hole lasers could reshape our technological future. This vision of harnessing energy from black holes brings us back to one of the most captivating aspects of theoretical astrophysics: the possibility of extracting usable energy from black holes. While current ideas about energy extraction focus on more conventional methods, such as the Penrose process, the discovery of black hole lasers would open entirely new avenues for energy manipulation. We might one day find ways to tap into these laser emissions, or perhaps even engineer black holes in the lab to produce controlled emissions of energy, similar to how we currently manipulate lasers on Earth. Such technologies could revolutionize our energy production methods, offering potentially unlimited clean power. Furthermore, black hole lasers challenge our assumptions about the role of black holes in the cosmic ecosystem. Traditionally, black holes have been seen as dead ends, regions where all matter and energy are consumed and lost forever. However, the idea of black hole lasers suggests that, far from being the ultimate sinks of energy, black holes might play an active, dynamic role in the cosmic cycle of energy. They could contribute to the growth of galaxies, regulate the formation of stars, and even influence the evolution of the universe itself. Looking beyond our own galaxy, the implications of black hole lasers could extend to the study of other galaxies and even intergalactic space. If black holes in distant galaxies exhibit laser-like behavior, it could be possible to detect this activity from billions of light-years away. This would not only give us a new tool for studying black holes in distant galaxies, but also provide a glimpse into the complex and energetic processes taking place in the cores of those galaxies. Moreover, studying black hole lasers could have profound effects on the field of astrophysics as a whole. By understanding how black holes interact with quantum fields in this novel way, we may unlock new avenues for exploring the fundamental forces of nature. The insights gained could help us understand the nature of dark matter and dark energy, resolve some of the outstanding mysteries of cosmology, and even pave the way for future breakthroughs in high-energy physics. Black hole lasers are far from just an exotic theoretical curiosity. They represent a profound shift in our understanding of black holes and the fundamental workings of the universe. As we continue to explore this concept, we may not only answer key questions about the nature of spacetime, gravity, and quantum mechanics but also unlock new technologies and methods for harnessing the power of the cosmos itself. While the road ahead is fraught with challenges and uncertainties, the potential rewards make the pursuit of black hole laser research one of the most exciting and promising areas of modern physics. As we continue to explore the intriguing possibilities presented by black hole lasers, it's important to consider their implications on the broader field of astrophysics and the future of space exploration. The potential discovery of black hole lasers would undoubtedly mark a paradigm shift in how we understand not only black holes but also the very fabric of the universe itself. As we've discussed, these phenomena challenge conventional ideas, pushing the boundaries of physics and creating new opportunities for technological advancements. But what would it truly mean for humanity if we were able to harness the energy produced by these enigmatic objects? One of the first challenges is the sheer scale of black holes. These cosmic giants range from a few times the mass of the Sun to supermassive black holes, which can be billions of times more massive. The energy released by a black hole laser, if detected, would likely be immense, potentially comparable to the energy output of entire galaxies. Harnessing this energy could offer possibilities for propulsion and power generation that are currently unimaginable, opening the door to interstellar travel and perhaps even intergalactic exploration. In fact, the idea of using black holes as cosmic energy sources may not be as far-fetched as it sounds. Scientists are already exploring the feasibility of extracting energy from rotating black holes through processes like the Penrose process, where energy can be released from a black hole by splitting a particle into two. The energy produced from such a process could theoretically be used as a power source. If black hole lasers become a reality, it would add an entirely new dimension to this research, suggesting that black holes could serve not only as energy sinks but also as energy generators, offering humanity an unprecedented opportunity to tap into cosmic forces. However, this brings us back to the core question: how would we go about detecting and understanding these black hole lasers in the first place? The search for these phenomena would require a leap in our observational capabilities. Current technologies like the Event Horizon Telescope, EHT, and gravitational wave detectors like LIGO and Virgo have opened new windows into the study of black holes. These instruments allow us to capture incredibly detailed images of black hole event horizons and detect the ripples in spacetime caused by massive objects like black holes merging. Yet, despite these advancements, detecting the faint radiation emitted by black hole lasers would still be a formidable task. One way to approach this challenge would be through the use of highly sensitive space-based observatories. Observing black holes in different wavelengths of light, including gamma rays, X-rays, and radio waves, could provide valuable information about their behavior. Space telescopes such as NASA's Chandra X-ray Observatory and the upcoming James Webb Space Telescope could play critical roles in revealing the hidden properties of black holes. These telescopes may eventually help us uncover the faintest signals that could indicate the presence of a black hole laser. If black hole lasers do exist, their detection would likely require years, if not decades, of careful observation and refinement of our observational techniques. Theoretical models of black hole lasers are still in their infancy. However, as our understanding of quantum mechanics and general relativity deepens, we may begin to see more sophisticated models emerge. These models could help predict the specific conditions necessary for the formation of a black hole laser. For example, certain theoretical frameworks suggest that a stable axion cloud or scalar field could be a key ingredient in generating these lasers. Understanding the dynamics of these fields and the extreme conditions near black holes would require cutting-edge simulations and computational models. As computational power continues to grow, these models will become more refined, offering insights into the precise mechanics behind black hole lasers. In addition, the potential discovery of black hole lasers could have profound implications for our understanding of the nature of light itself. Traditional lasers, as we know them, are highly controlled systems where light is amplified through a process known as stimulated emission. The notion that black holes might produce a similar form of coherent radiation suggests that the laws governing the interaction of light with matter could be far more intricate than we currently realize. If black hole lasers do indeed exist, they could force physicists to revisit the foundations of laser theory, potentially revealing new insights into the behavior of photons and their interaction with gravity. The quest for black hole lasers is not just about understanding black holes, though. It is also about understanding the fundamental nature of the universe. The existence of these lasers would imply that black holes are not passive objects but are active players in the cosmic drama, influencing their environment in ways we are only beginning to comprehend. The feedback loops between black holes and their surrounding environments could have far-reaching implications for the evolution of galaxies, the formation of stars, and the large-scale structure of the universe. By studying these phenomena, scientists may be able to answer fundamental questions about the life cycle of galaxies, the distribution of dark matter, and the role of black holes in the broader cosmic ecosystem. Moreover, the potential for black hole lasers could drive technological innovation in ways we cannot yet predict. The harnessing of black hole energy, whether through lasers or other processes, could enable the development of technologies far beyond what we can imagine today. Concepts like faster-than-light travel, energy-efficient propulsion systems, and advanced space habitats could become more achievable as we learn how to tap into the extreme forces present near black holes. These advances could pave the way for humanity's future as an interstellar species, allowing us to venture beyond our solar system and explore the vast reaches of the universe. As we look toward the future, the study of black hole lasers could also become a unifying thread in the broader field of fundamental physics. The challenges posed by these objects span across multiple domains of science, from quantum mechanics and general relativity to high-energy astrophysics. Studying black hole lasers could help bridge the gap between these disparate areas of research, ultimately leading to a more unified understanding of the forces that govern our universe. This quest for knowledge could usher in a new era of discovery, where the boundaries between different fields of science are blurred and new, groundbreaking theories emerge. Black hole lasers may hold the key to answering some of the most profound questions in science. How do black holes interact with quantum fields? What role do they play in the evolution of galaxies and the universe as a whole? And perhaps most tantalizing of all, what are the fundamental properties of the universe that we have yet to discover? While black hole lasers may still be a theoretical concept, their potential to revolutionize our understanding of the cosmos is undeniable. As we continue to explore the mysteries of black holes, the possibility of encountering these cosmic phenomena serves as a reminder that the universe is far more strange and wondrous than we could have ever imagined. The implications of black hole lasers, once confirmed, would likely extend far beyond our current scientific understanding, leading to new technological advancements and potential shifts in our approach to space exploration. However, the road to discovering black hole lasers is paved with challenges, both observational and theoretical. As scientists continue to probe the depths of black holes, they may encounter unexpected phenomena that could offer new insights into the behavior of matter and energy in the most extreme environments. These discoveries might even redefine what we thought we knew about the very nature of space and time. One critical factor in the study of black hole lasers is the relationship between black holes and the surrounding accretion disk. The accretion disk, composed of gas and other materials spiraling into the black hole, plays a significant role in the dynamics of the black hole system. When materials in the accretion disk are heated to extreme temperatures, they can emit radiation across a wide spectrum, from X-rays to radio waves. This radiation is often the result of interactions between the material and the immense gravitational and magnetic forces near the event horizon of the black hole. The interaction between these forces could potentially lead to the amplification of light, a key feature of laser behavior. Understanding this process requires delving into the complex nature of black hole accretion and the behavior of materials in the presence of intense gravitational fields. Some theorists propose that under certain conditions, a black hole's accretion disk could act like a cosmic laser, focusing energy and directing it in a highly concentrated beam. If this model holds true, then the energy emitted by black hole lasers could be far more powerful than anything we have ever observed in the universe. The sheer amount of energy produced would have vast implications for the fields of astrophysics and energy science. However, for scientists to fully grasp the dynamics of black hole lasers, they will need to build on the existing theoretical frameworks surrounding black hole physics. The study of black holes is already a highly specialized field, drawing on the principles of both general relativity and quantum mechanics. Black holes are thought to be regions of space where gravity is so intense that nothing, not even light, can escape. Understanding how light could be amplified and concentrated near a black hole would require a deeper integration of these two theories, an area of physics that remains one of the greatest unsolved puzzles in modern science. If the mechanism behind black hole lasers can be explained within the context of these theories, it could represent a monumental breakthrough, offering answers to some of the most profound questions about the universe. One such question revolves around the nature of the event horizon. The event horizon of a black hole marks the boundary beyond which nothing can escape, not even light. However, the study of black hole lasers suggests that the region near the event horizon could still be highly dynamic, potentially allowing for the amplification of light. This raises questions about the behavior of spacetime in this region, particularly in relation to quantum fields and the strange effects that arise from the intense gravitational forces near a black hole. The discovery of black hole lasers could provide a window into these previously inaccessible regions, helping scientists better understand the interplay between gravity, light, and quantum fields. Another intriguing aspect of black hole lasers is their potential connection to dark matter and dark energy. These mysterious substances make up a vast majority of the universe's mass and energy, yet we have little understanding of their nature. If black holes are capable of generating intense energy through processes like laser emission, it is possible that this energy could be related to the mechanisms driving the expansion of the universe. Some theorists have speculated that dark energy could be linked to the behavior of black holes, with the emission of laser-like radiation being a key piece of the puzzle. While these ideas remain speculative, they highlight the interconnectedness of the forces at play in the cosmos and the potential for black hole lasers to unlock new insights into the nature of dark matter and dark energy. Furthermore, the study of black hole lasers could have a profound impact on our understanding of the fundamental nature of time. One of the most mind-bending aspects of black holes is their ability to warp spacetime itself. As objects approach a black hole, time appears to slow down due to the extreme gravitational effects. Theoretically, this warping of time could have implications for the behavior of light near a black hole, potentially allowing for the creation of a focused beam of energy that behaves similarly to a laser. This interplay between gravity, light, and time is one of the most fascinating aspects of black hole physics, and the discovery of black hole lasers could offer a new perspective on these exotic phenomena. In addition to their theoretical significance, black hole lasers also hold the potential for practical applications in the distant future. If scientists are able to harness the energy produced by these lasers, it could revolutionize our understanding of power generation. Current energy sources, such as solar power, nuclear energy, and fossil fuels, have limitations in terms of scalability and sustainability. In contrast, the energy emitted by a black hole laser could be nearly limitless, offering a potential source of power that is both incredibly efficient and abundant. While harnessing such energy remains a distant prospect, the theoretical possibilities are both exciting and humbling, offering a glimpse into a future where humanity taps into the most extreme forces of the universe. The idea of using black holes as a power source also raises questions about the ethical and environmental implications of such technology. The sheer scale of energy involved in black hole lasers could have far-reaching consequences for the cosmos, potentially affecting the structure of galaxies and the fate of nearby star systems. As with any new technology, the potential benefits of harnessing black hole energy would need to be weighed against the risks. Could such a discovery lead to unforeseen consequences for the balance of the universe? These are the kinds of questions that scientists, ethicists, and policy makers will need to consider as the study of black hole lasers progresses. As we stand at the edge of this exciting frontier in astrophysics, one thing is clear: black hole lasers represent a tantalizing possibility that could reshape our understanding of the cosmos. Whether they are eventually detected or remain a theoretical concept, they serve as a reminder of the infinite potential for discovery that lies within the universe. By studying these enigmatic objects, we are not just unraveling the mysteries of black holes, we are also probing the very limits of human knowledge, seeking answers to questions that have long eluded us. In the coming decades, as observational technologies continue to improve and theoretical models become more sophisticated, we may finally have the tools necessary to detect and study black hole lasers in detail. The journey to uncover this hidden aspect of the universe may be long and fraught with challenges, but the potential rewards are beyond imagination. With each new discovery, we inch closer to unlocking the secrets of black holes and the mysterious forces that govern the cosmos. And who knows? Perhaps the black hole lasers we now only dream of could one day become an integral part of humanity's quest to explore and understand the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.